A very good morning to one and all. On behalf of Department of Chemistry, Vijayagarh Jyotish Rai College, I extend my warmest welcome to the honorable speakers, our respected principal madam, all faculty members, research scholars, and my dear students in today's international webinar on recent advances in chemistry and chemical biology, organized by Department of Chemistry and IQAC of Vijayagarh Jyotish Rai College. Hope this webinar will be enlightening for all of us. Now, I would like to invite Dr. Dashrath Mal, the convener of today's international webinar, to tell something regarding this webinar. Sir, please.
Good morning, everybody. Our respected Principal Madam, invited speaker, and all the participants. I express my sincere thanks and heartfelt gratitude to our Principal Madam for her continuous support and constant encouragement to organize this webinar. I also express my sincere thanks and gratitude to IQAC coordinator Dr. Prasenjit Das and all the faculty members of Department of Chemistry for their valuable suggestion and active participation. I express my special thanks to Mr. Anupam Choudhury, Faculty Department of Chemistry, for technical support and valuable suggestion and active participation to organize this webinar. I express my heartfelt gratitude to our invited speaker, Professor Dr. Nitin Chattopadhyay from Jadavpur University, Dr. Nimai Chandra Pramanik from Glass and Ceramics, Kolkata, Dr. Naim Sepai from Lady Braven College, Dr. Nirnoy Samanto from Germany for accepting our invitation. I also express my sincere thanks to all the participants from different colleges, universities, research institute, and to my beloved student. This seminar aims to bridge the gap between the scientists and the young UG students, PG students, by exposing them to the scientific seminar and encouraging them to participate and interact with renowned scientists working in the different fields in the different part of the country and abroad. I am sure, especially our younger researcher and my beloved students will get opportunity to interact with our invited speaker and lecture delivered by our invited speaker and oral presentation of different faculties from different universities and colleges will enrich them, and our student will get more inspiration and the seminar becomes grand success. Thank you.
Thanks a lot to Dr. Dashrath Mal for his wonderful inaugural speech. Now we will start the technical session. Our first speaker is Professor Nitin Chattopadhyay from Jadavpur University. I would like to invite our respected HOD Madam, Dr. Shumita Rai, to chair the session and to introduce Professor Chattopadhyay. Madam, please.
Thank you, Anindita. Good morning, everyone. I, Dr. Shumita Roy, feel extremely proud to be a part of today's webinar. It gives me immense pleasure to start this auspicious occasion by heartily welcoming all of you. First of all, I thank Dr. Dasharat Mal, Dr. Devopon Sinha, and Anupam Chaudhuri for organizing such an amazing international webinar entitled Recent Advances in Chemistry and Chemical Biology. I welcome our respected Principal Madam, Dr. Rajyasree Neogi, for always encouraging us to organize this type of webinar. It gives me great honor and pleasure to introduce our today's first speaker, Professor Nitin Kumar Chattopadhyay, who has come to grace our today's occasion. I feel elated to introduce him to everyone. Professor Nitin Chattopadhyay obtained his BSc and MSc in chemistry from Calcutta University and PhD from Jadavpur University, working with Professor Mihir Chaudhuri at Indian Association for the Cultivation of Science, Kolkata. He joined Jadavpur University in 1991. During postdocs, he visited Katholieke University Leuven, Belgium, Coimbra University, Portugal, and Osaka University, Japan. His achievements have been recognized by many awards. Fellow of the Indian Academy of Sciences, FASC, Fellow of the National Academy of Sciences, India, FNASC, Fellow of the West Bengal Academy of Science and Technology, FASCT, Bronze Medal from Chemical Research Society of India, CRSI, Shiksha Ratna Award from Government of West Bengal, Professor S.C. Ameta Award from Indian Chemical Society, Professor S.R. Mohanty Award from Odisha Chemical Society. He is also the member of the Joint Academy, INSA, IASC, NASI, Science Education Panel 2016. Professor Chattopadhyay has been in the editorial boards of Biophysical Chemistry, Journal of Colloid and Interface Science, Journal of Photochemistry and Phytobiology, Biology, Journal of Luminescence, Helion, and Journal of Chemical Sciences. He has completed 11 research projects, CSIR 5, DST India 5, DBT 1. Near about 20 students have obtained their PhD degree under his supervision. His publications is near about 180. Keynote plenary invited talks is about 170. However, today we are here to recognize Professor Chattopadhyay's outstanding talent as a professor, as a research guide, as a scientist, etc. Sir, thank you for taking out time for all of us from your busy schedule. Once again, I welcome you to this webinar. We all are keen to hear your innovative lecture today. Over to you, Professor. Thank you.
Am I audible?
Yes, sir.
Okay.
Yes, sir.
Still good morning. First, thank you, Professor Mann, for the nice introduction and very big one also, which is unnecessary. The title of today's international webinar is Recent Advances in Chemistry and Chemical Biology. Of course, I have a reasonable amount of scientific works in both the fields, like chemistry as well as chemical biology. But basic to all these is the learning of the subject. So today I will present myself more as a teacher than as a researcher. And I took the permission of Dr. Mal in this regard, and I will present, you will get it shortly. I will present a demo type talk representing how to learn and also how to teach. So my talk will address to both the students community as well as the teaching community. So without wasting time, Let me start. So, for the students, this is your homework. How to do this? This is simply water, right? And this is a paper. Okay. So the topic may be something like attitude of learning and teaching. How to learn? Yes. Sorry. Sorry. Oh, yes.
তোমার কি গো রবিবার দিন আমার এগো এগো কোথায় আসবে না তো
Region now. Sorry. Yes. Your enter screen. Then here. Now I go there. Is it visible? Is it visible now?
Yes, sir.
Yes, sir.
I'm sorry for this technical inability at the beginning. So this remains the task of the students' homework. How can you make this thing? So these footprints are of water and this is paper. So you can just do some exercise on it. The title can be something like attitude of learning and teaching. In my life, I have understood that this attitude, this word is the most important word in anyone's life. If one can tune his or her attitude properly, then this attitude, that's it. So this is me, and please do not hesitate to contact me directly over phone or at this email address. Phone number is available in web page also. So just go to Google, type my name, it will be directed to my homepage. That's it. Okay. First, my humble submission, particularly to the seniors and the teachers. I do not intend to give you lessons. I am not capable to do that, but wish to share my realizations, hardcore realizations. That's it. So please take it that way, in a positive sense. And now let us start with a famous quote by none other than Professor Dr. APJ Abdul Kalam, our ex-president of India. What he said, all birds find shelter during rain. When a rain starts, the bird generally try to find some shelter, some guarded place. Okay, but eagle doesn't do it. Eagle avoids rain by flying above the clouds. So when it starts raining, the eagle starts flying up, and eventually it crosses the level of the layer of the clouds. So that is the way eagle adopts. So what is the take-home message from here? You see, problems are common to all. All the birds are facing the rain, but attitude makes the difference, right? Okay. By the way, I just asked Professor Mal if I will deliver this thing in English or a mixed language, and he advised or he suggested to take me in the second one. So I will do that. So there will be, of course, Bengali and English. Now, I am very much fond of, or rather, I like to read the T-shirt writings. In one, I saw this thing. I was born intelligent. Education ruined me. I believe it to be correct to a good extent. Of course, there may be some adjective here that is incorrect or improper education, which is given, which is delivered by many of the schools, unfortunately, by people like us, the teachers. So I was born intelligent because I had a lot of questions. All the kids, they asked continuously. But then, after going to the school, maybe 5, 6, 7, 8, and exponentially the questioning, the attitude of questioning that decreases. And when he or she comes to the graduation level in our place, they don't have any question. So that is the way that I feel that education ruined. Now, what is the objective of education? Because in the just previous slide, we have stated that education. So what is the objective of education, or what is the purpose of education? Some certificates, some pass degree certificates, mark sheets, etc. Cannot be. No, to me, objective of education is to enhance the power of logical thinking. So logical thinking is very important. Okay. So if there are people who are real in proper sense educated, there will be no quarreling, there will be no fight, there will be no ego, nothing, because they are not logical things. So we should try always to be educated, not well informed. Okay. Now we should know that teachers are the makers of the society. This is my own statement. You see, we have some makers of the society like teachers, doctors, engineers, technicians, all sorts of things. But teachers are the persons who have taught all those individuals. So all of these categories that I just mentioned, they have been taught by teachers. So teachers are the makers of the society. Then teachers are the most respected persons of the society even today. That is my real experience. So we are privileged in that sense. And whenever we are privileged, obviously associated to that, we have our responsibilities and duty. So we should do these things. Otherwise, we are going to lose our respect that we earn or that we get from the society. Now, points to feel and follow. To feel the need of good teachers. There is a statement which says, like, if you want to damage a society, simply damage the education system. That's it. You don't need to do anything else. So that there lies the importance of good teachers. Then all the teachers and even the societal people, we should accept that teacher is not a superman or superwoman. So we have to admit, even the teachers should admit, I do not know, wherever it applies. But of course, if to any students we always use this thing, I do not know, that is not the way. That is not the message of my statement. In some cases, in some typical new questions, situation may arise that I do not know. Then please do not hesitate to say that I do not know, but I will get in touch with you maybe tomorrow. Okay? And that helps. Students are the best teachers. So, to let them think and question. ছাত্রদেরকে অ্যালাউ করতে হবে তারা নিজের মতো করে চিন্তা করুক, কোশ্চেন করুক। Job of this is my feeling. Job of a teacher is not just to teach and finish the syllabus, but to create interest in the subject. That should be the job. যদি আমি নেশা ধরিয়ে দিতে পারি সাবজেক্টে, ক্রিয়েট ইন্টারেস্ট। যদি আমি নেশাটাকে কিন্তু পজিটিভ সেন্সে ইউজ করছি, প্লিজ মাইন্ড ইট। আমি যদি নেশা ধরিয়ে দিতে পারি একটা সাবজেক্টের উপর, একটা টপিকের উপর, তখন ছাত্রছাত্রী তারা নিজেরা ওই নেশার ঘরে আমাকে প্রশ্ন করবে, অন্য টিচারদের প্রশ্ন করবে, পড়াশুনো করবে, তারা আমাদেরকে চাইবে, ইউজ করবে। সেইটা দরকার। শুধুমাত্র আমরা যদি নোট ডেলিভার করি, লেকচার দিয়ে বেরিয়ে আসি, ইন্টারাক্ট না করি, তাহলে কিন্তু তার এফেক্টটা খুবই কম হয়। There is a contrast, drastic contrast between class lecture and political lecture. What is that? You see, this is webinar, so I cannot directly interact, and I cannot read your faces. That's the problem with webinar. Anyway, we have to accept the situation. The main difference that I feel is class lecture it should be bi-directional, and political lecture only unidirectional. The boss, political boss of course, says something blah, mostly rubbish, and nobody dares to put any question. So the take-home message is teaching is a reversible process. So every class should be reversible. The participative mode should be there in any class. Now, some other features also. This is pertinent to both students as well as teachers. For the teachers, this is important to read the faces of the students. Whenever there is direct class, not webinar-like thing or online class, when it is real class, please try to read the faces, and that will give you a feedback that whether the students are getting your teaching or not. তারা বুঝতে পারছে কিনা সেটা তাদের মুখ দেখে বোঝা যাবে, বিকজ ওদের মুখটা হচ্ছে আয়না, ভিতরের আয়না। Then a scientific statement must be complete within itself. আমরা কখনো কখনো জাস্ট হালকা করে একটা সেন্টেন্স বলে দিই, scientific statement should not be given that way. A scientific statement must be complete within itself. যেমন আমি একটা এক্সাম্পল দিই, জলের pH 7, এটা একটা সায়েন্টিফিক স্টেটমেন্ট হতে পারে না, যে কোনো টেম্পারেচার এটা 7 হবে না। তাহলে আমাকে বলতে হবে at 25 degrees centigrade pH of water is 7. That's it. That is scientific statement, but not the other one. Scientific terms should be kept in English. Integration, differentiation. আমি বাংলাতে লিখতে পারি, কিন্তু বাংলাতে ওই ডিফারেন্সিয়েশন এটাই লিখবো। Scientific terms should not be translated in regional language. Viscosity, it should be written in Bengali script. Viscosity. Surface tension ওভাবে লেখা উচিত, সারফেস টেনশন বাংলাতে, কিন্তু সারফেস টেনশনকে সান্দ্রতা বলাটা একেবারে ঠিক নয়। কারণ যখন আমরা ন্যাশনাল লেভেলে কোনো জায়গাতে যাব, আমাদের বিভিন্ন রকম ল্যাঙ্গুয়েজ আছে, অ্যান্ড ইট উইল মেক এ মেস। আর ইন্টারন্যাশনাল কেসে এটা ঝামেলা আরো বেশি হবে না। সুতরাং ইংলিশ ইজ দ্য সেফেস্ট ল্যাঙ্গুয়েজ, at least for the scientific terms. Don't try to change it or convert it into regional language. আর একটা খুব ইম্পর্টেন্ট পার্ট, এটা বোথ ক্লাস অফ পিপল, মানে স্টুডেন্টস এবং টিচার উভয়ের ক্ষেত্রে প্রযোজ্য, টু কোরিলেট সায়েন্স উইথ সোসাইটি অ্যান্ড ভাইস ভার্সা। সায়েন্সে বইয়ে যেগুলো পড়ছি তার সঙ্গে সোসাইটির কোথায় কোথায় মিল আছে সেটা দেখতে হবে, তাহলে আমাকে মুখস্থ করতে হবে, ওটা থেকে যাবে। আবার সোসাইটির কিছু কিছু থেকে আমি সায়েন্সে কনভার্ট করে বইয়ে পেতে পারি, সেগুলো দরকার, এটা খুবই ইম্পর্টেন্ট। মেসেজেস ফর দ্য স্টুডেন্টস, রিড লেস, ইউ রিড এ লট। হায়ার সেকেন্ডারির সময়, মাধ্যমিকের সময় তোমরা কন্টিনিউয়াসলি স্টুডেন্টরা পড়াশোনা করে গেছে, এক টিচারের কাছ থেকে আরেক টিচার, তারপর স্কুল, আবার ফিরে এসে টিচার। যদি এতটাই পড়াশোনা করো ওইভাবে, নিজে চিন্তা করবে কখন? আজ রিড লেস, থিঙ্ক মোর, দিস ইজ মোর ইম্পর্টেন্ট, যেটা আমি বিলিভ করি এবং আমি নিজে ফলো করেছি। আমি এমন কোনো অ্যাডভাইস কাউকে দিই না যেটা আমি নিজে জীবনে ফলো করিনি এবং উপকারটা পাই। বই বন্ধ করে পড়াটা হচ্ছে মোর ইম্পর্টেন্ট দেন বই খুলে পড়া। আমাদের সায়েন্স স্টুডেন্টদের অ্যাটলিস্ট হায়ার সেকেন্ডারি লেভেলে একটা ফিলিং আছে যে সায়েন্স বইটা খুললেই সায়েন্সটা এসে গেল আমার কাছে, বন্ধ করলেই সায়েন্সটা চলে গেল। আসলে কিন্তু আমি একটা স্টেটমেন্ট ইউজ করি, সায়েন্স বুকস ডু নট কন্টেন সায়েন্স। আমি আসছি সেটা কতগুলো জেনারেল জিনিস, এটা ছাত্রদের প্রতি, অবশ্যই টিচাররাও এর মধ্যে ইনভলভ, বিকজ টিচার্স আর অলওয়েজ স্টুডেন্টস থ্রুআউট দেয়ার লাইফ। আস্ক কোশ্চেন্স, আস্ক কোশ্চেন্স, আস্ক কোশ্চেন্স। আমি মনে করি প্রশ্ন না করে কখনো কোনো সাবজেক্ট জানা যায় না, সায়েন্টিস্ট হওয়া তো দূরস্থান। এবং আমি মনে করি যখন প্রশ্ন নেই, হি অর সি ইজ লাইক এ ডেড পারসন। কারণ একটা চেয়ার টেবিল, এগুলো ডেড। চেয়ার টেবিল কখনো প্রশ্ন করে না। হিউম্যান বিং অবশ্যই সবসময় প্রশ্ন করবে, প্রথমে নিজেকে করবে। ফর দ্য স্টুডেন্টস, ইন্টারেক্ট উইথ দ্য টিচার্স। আর একটা ইম্পর্টেন্ট থিং, try to rationalize before accepting the lessons delivered even by the teachers. ছাত্রদের একটা ধারণা থাকে টিচাররা যা বলেন সব একদম খাঁটি, না, এটা ঠিক নয়। অন্তত পক্ষে সব টিচার যা বলেন তা তো নয়। সুতরাং কিভাবে করতে হবে, কি করবে তোমরা প্রথমে শোনো, শুনে নিজে অ্যানালাইজ করো, লজিক্যাল অ্যানালিসিস। যদি মনে করে হ্যাঁ এটা ঠিকই, তো তখন অ্যাকসেপ্ট ইট অ্যাজ সাচ। কিন্তু যদি মনে হয় if there is, you find some fallacy, some gap, then just interact with the teacher. তাকে বলো যে স্যার এটা তো এরকম, মানে কিন্তু অ্যাকচুয়ালি তো এরকম, and resolve the case. ওকে? আর যে টিচাররা যা, এমনকি আমিও যা বলছি সব অ্যাজ সাচ অ্যাকসেপ্ট করো না, প্রশ্ন করো নিজেকে, এটা ঠিক বলেছি কি না, যদি ঠিক বলে থাকি তাহলে ফলো করো, যদি না মনে হয় আর্গুমেন্ট করো। আর্গুমেন্ট ইজ নট ইকুয়াল টু কোয়ার্লিং। আর্গুমেন্ট ইজ হ্যাজ এ পজিটিভ মিনিং, কোয়ার্লিং হ্যাজ এ নেগেটিভ মিনিং। ওকে, some other simple advices: do household jobs yourself. কাজ করো, ঘরের কাজ করো, সেইখান থেকে সায়েন্স আছে। সায়েন্স ভিজুয়ালাইজ সায়েন্স দেয়ার, ওখান থেকে সায়েন্স আছে। গেট এক্সাম্পলস, এক্সাম্পলস মানে সায়েন্টিফিক এক্সাম্পলস ফ্রম ডে টু ডে লাইফ এক্সপিরিয়েন্স। এটা সিম্পল এক্সাম্পল আমি যদি বলি, ফিজিক্স এবং কেমিস্ট্রি, বেশিরভাগ ক্ষেত্রে ছেলেপুলেরা ফিজিক্সটাকে বেশি পছন্দ করে, অ্যাটলিস্ট হায়ার সেকেন্ডারি লেভেলে। কেন? কারণ ফিজিক্সের জিনিসগুলো দেখা যায়। দুজন ছাত্র বসে আছে, এ আর বি, হঠাৎ কোনো কারণে এ বিকে একটা ঘুষি মারলো, সঙ্গে সঙ্গে কিন্তু বি জানতে পারলো হোয়াট ইজ ফোর্স, রাইট? এইটা যে রিয়েল এক্সপিরিয়েন্স, বইয়ে ফোর্স পড়ে কিচ্ছু বুঝবো না। এই যখন ঘুষিটা মারলো তখন সে বুঝতে পারলো এটা। এই এ হয়তো তাকে বললো এটাকে ফোর্স বলে, বুঝলি? ও পরিষ্কার বুঝে গেল। এবং নিডলেস টু সে, এ যে কিনা মেরেছিল বিকে, এ সঙ্গে সঙ্গে জানতে পারবে হোয়াট ইজ থার্ড ল অফ নিউটন, নিউটন থার্ড ল, তাই না কি? আচ্ছা, ফাইন্ড সায়েন্স আউটসাইড ইউর সায়েন্স বুকস। যেটা আমি বললাম, আই স্ট্রংলি বিলিভ, I just tell boldly, science books do not contain science. তাহলে what do they contain? Let me establish this thing. মনে করো একটা, আমি ছাত্রদের উদ্দেশ্যে তুমি করে বলছি, টিচাররা প্লিজ ডোন্ট মাইন্ড। মনে করো একটা মেঝে আছে, একটা ফ্লোর আছে, সেই ফ্লোরে কোনো এক দুই বন্ধু আছে, কোনো এক বন্ধু ইচ্ছা করে হোক বা অনিচ্ছাকৃত ভাবে কিছুটা তেল ফেলে রেখেছে, সর্ষের তেল ফেলে রেখেছে মেঝের উপরে। এবার তার অন্য বন্ধু দৌড়ে দৌড়ে আসছে, কি হবে? স্লিপ করে পড়ে যাবে। কেন পড়লো? আমরা সবাই জানি, ছাত্ররা সবাই জানে যে ফ্রিকশনটা কমে গেছে। দ্যাট ইজ অ্যাকচুয়ালি সায়েন্স। এবার বলো তো, ওই সায়েন্সটা কি বইয়ে আছে? না তো। এবার তাহলে সায়েন্স বই, এত মোটামোটা কেমিস্ট্রি বই, ফিজিক্স বই, বায়োলজি বই কি আছে? সায়েন্টিফিক অবজারভেশন, সায়েন্স যেটা অ্যাকচুয়ালি তোমার মধ্যে এবং তোমার আশেপাশে ঘটছে, সেইগুলোকে লেখা আছে, কালেকশন করা আছে। এবং সেটাকে প্রমাণ করার জন্য কিছু এক্সপেরিমেন্ট ডিজাইন করা আছে, যেগুলো বাইরে অ্যাকচুয়ালি কেউ করেছেন, ডিজাইন করা আছে, তার এক্সপ্লেনেশন দেওয়া আছে, তার ম্যাথমেটিক্যাল ডেরিভেশন আছে, এইসব। তাহলে সায়েন্স অ্যাকচুয়ালি নেই তোর মধ্যে। সায়েন্সটা, সায়েন্স টেক্স প্লেস উইদিন ইউ অ্যান্ড অ্যারাউন্ড ইউ। কাজে ওই সায়েন্সটা যদি আমি না দেখি, আমি যদি চোখ বন্ধ করে থাকি, শুধু সায়েন্স বই খুলে কিচ্ছু হবে না, শুধুমাত্র ইনফরমেশন হবে। অ্যান্ড ইনফরমেশন ডাজ নট লাস্ট লং, কদিন পরেই ভুলে যাবে। যে কারণে যেগুলো হায়ার সেকেন্ডারিতে পড়ে এসছো, এখন জিজ্ঞাসা করলে, কলেজ লেভেলে জিজ্ঞাসা করলে অনেকেই পারো না, সবাই নয়। ন্যাশনাল জিওগ্রাফিক, ডিসকভারি সায়েন্স, এই চ্যানেলগুলো দেখো, অনেক কিছু শিখতে পারবে। ওয়াচ মুভিজ লাইক 3 Idiots. I believe most of you, maybe 95% or more, have visited this or have seen this, have enjoyed this movie, 3 Idiots. Now that is not all. And get the take-home message or messages. What is the take-home message from this movie? Of course, this is a subjective question, so answers will vary definitely. But to me, the main message, take-home message, you can have or we can have from Rancho's speech. In one place, Rancho says, "Kabil bono." In Hindi, of course, I have written it in Bengal, in English, but it was Hindi language. काबिल बनो, कामयाबी झक मार के आपके पीछे आएगी। তুমি নিজে কাবিল হও, অর্থাৎ সক্ষম হও, এক্সেল করো। তাহলে এটাকে যদি আমি ইংরেজিতে কনভার্ট করি, গো ফর এক্সেলেন্স, সাকসেস উইল ফলো ইউ। তোমাকে সাকসেসের পিছনে দৌড়তে হবে না। এটা অনেকটা সেই খুঁড়োর কল, সুকুমার রায়ের খুঁড়োর কল, সামনে এখানে কাঠ দিয়ে বাঁধা আছে, এখানে আঙুর আছে, তোমাকে বলা হচ্ছে আঙুরটা খাই, ওটা হচ্ছে সাকসেস। তুমি দৌড়াও দৌড়াও, কিছুতেই পাবে না, কারণ এই গ্যাপটা তো ফিক্স। এ দুলবে কিন্তু তাও আসবে না মুখ পর্যন্ত। এটা হচ্ছে আমরা যেটা করছি, তোমরা যেটা করছো, সাকসেসের পিছনে দৌড়ছো, তা নয়। নিজেকে, যেটা 3 Idiots এর মেসেজ, ওইটা নিজেকে সমর্থ, সক্ষম বানাও, উন্নত করো। অ্যাকচুয়ালি এই দুনিয়াতে এই পৃথিবীতে সবচেয়ে বড় কম্পিটিটর কে জানো? তোমার আজকের তুমি, গতকালের তুমি, আজকের তুমি, আগামীকালের তুমি এর মধ্যে কম্পিটিশন করো। গতকালের তুমি থেকে আজকে তুমি যেন বেটার হয়, আজকের তোমার থেকে যেন আগামীকালের তুমি বেটার হয়। দ্যাট ইজ দ্য রিয়েল কম্পিটিশন। ওকে, ডু নট টেক সায়েন্স অ্যাজ সামথিং টু রিড অ্যান্ড লার্ন। জাস্ট বই পড়লাম, সায়েন্স বই খুললাম, সায়েন্স এসে গেল, বন্ধ করে দিলাম, সায়েন্স নেই। ডোন্ট বিহেভ লাইক দ্যাট, ডোন্ট ডু দ্যাট। Accept it as a game and enjoy it, playing games. Like play happily with science. যেমন আমি বলছি, আনফর্চুনেটলি আজকাল ছেলেপুলেরা, বাচ্চারা বাড়িতে সায়েন্স নিয়ে খেলা করে না, সায়েন্স নিয়ে গল্প করে না, সায়েন্স নিয়ে জোক করে না, সায়েন্টিস্টের লাইফ করে না। এগুলো খুব নেগেটিভ বা ডেরোগেটরি একটা সিচুয়েশন হয়ে গেছে। প্লেস হ্যাপিলি উইথ সায়েন্স। যেমন আমি বলছি, সূচ সেলাই করার সূচ কখনো জলে ভাসিয়েছো? খাও। কাগজের পাত্রে কখনো ভাত রান্না করেছো? কাগজের পাত্রে এই যে ফ্লোট সিউইং নিডল, সেলাইয়ের যে নিডল সূচ, ফ্লোট ইট অন ওয়াটার সারফেস, জলের উপর ভাসিয়ে দাও। তো যদিও জানো, আমি যদি ধরে নিই নিডলটা লোহার তৈরি, তাহলে লোহার ডেন্সিটি অনেক বেশি জলের থেকে, কিন্তু ওটাকে ভাসানো যায়। সেটা করো, এটা প্র্যাকটিস করো, এটা খেলা করো। সায়েন্সের প্রতি ইন্টারেস্ট আসবে। সায়েন্সকে যতক্ষণ না ভালোবাসবে, সায়েন্স তোমার সঙ্গে থাকবে না। আমি আসছি সেক্ষেত্রে। বয়েল রাইস ইন এ পেপার পট, একটা কাগজের পাত্রে ভাত তৈরি করো। এই ভাত তৈরি করা মানে কিন্তু এরকম নয় যে বাড়ির 3 জন পেট ভরে খাবে, সেটা নয়। 4টে চাল নাও, 5টা চাল নাও, 10টা চাল নাও, সেই চালের ভাতটা। সায়েন্সটা ওখানে। অর্থাৎ আমি জল বয়েল করছি করছি করছি, জলটা বয়েল করেই যাচ্ছে, একসময় চালটা সিদ্ধ হয়ে যাবে, ভাত হয়ে যাবে। এটা সম্ভব কি? কাগজের প্লেটে সম্ভব। আমি যেগুলো বলছি সবই সম্ভব, আমি নিজে করেছি। তোমরা যে কেউ আমার সঙ্গে কন্ট্যাক্ট করলে আমি বলে দেবো কিভাবে করতে হয়, বাট নিজের আগে চিন্তা করো। আমরা অবশ্যই কতগুলো জিনিস অ্যাভয়েড করতে পারি না, সেটা হচ্ছে প্রবলেমস। দেয়ার আর অলওয়েজ প্রবলেমস দ্যাট উই ডু ফেস, বিশেষ করে টিচারদের পক্ষে এটা প্রযোজ্য। ক্রাউডিং অফ স্টুডেন্টস ইন এ ক্লাস, একটা ক্লাসে 70 জন স্টুডেন্ট আছে, আমরা কি করে 1 ঘন্টার ক্লাসে বা 45 মিনিটের ক্লাসে সকলকে ইন্ডিভিজুয়ালি নজর দিতে পারবো? সম্ভব না। ক্রাউডিং অফ স্টুডেন্টস ইন ক্লাস, লোড অফ সিলেবাস, এই টাইমের মধ্যে সিলেবাস শেষ করতে হবে, তার মধ্যে এত ছুটি, এত প্রোগ্রাম ইত্যাদি ইত্যাদি। ল্যাক অফ ইনফ্রাস্ট্রাকচার অ্যান্ড ফেসিলিটিস লাইক অডিও ভিজুয়াল, যেমন টিভি, রেডিও থেকে টিভি অনেক বেশি ইম্পর্টেন্ট, অনেক বেশি, তার অ্যাপিল বেশি, অনেক বেশি অ্যাট্রাক্ট করে। সেই সিস্টেম কিন্তু বেশিরভাগ স্কুলে নেই। এইরকম হচ্ছে ল্যাক অফ ইনফ্রাস্ট্রাকচার। ল্যাক অফ ফেসিলিটি অফ হ্যাভিং অ্যাক্সেস টু জার্নাল অফ কেমিক্যাল এডুকেশন, কিছু কিছু ইন্টারন্যাশনালি ফেমাস জার্নাল আছে এডুকেশনের জন্য, স্কুল স্টুডেন্ট বা কলেজ স্টুডেন্টের জন্য। যেমন একটা আছে, সবচেয়ে ভালোটা হচ্ছে জার্নাল অফ কেমিক্যাল এডুকেশন, পাবলিশ বাই আমেরিকান কেমিক্যাল সোসাইটি। এই জার্নালগুলো বেশিরভাগ স্কুলে অ্যাভেলেবল নয়। এক্সটার্নাল ডিস্টারবেন্সেস আর অলওয়েজ দেয়ার, লাইক ডিকুইশন অফ একাডেমিক ইনস্টিটিউশনকে এই কোনো একটা বিয়ে বাড়ির জন্য নেওয়া হলো, অমুক পুজোর জন্য নেওয়া হবে, অমুক পলিটিক্যাল একটা প্রোগ্রাম হবে, তার জন্য একদিন নেওয়া হলো, এইরকম ডিকুইশন অফ একাডেমিক ইনস্টিটিউশনস ফর পলিটিক্যাল অ্যান্ড আদার রিজনস। অফ কোর্স ইউ নো অল, প্রপার রিক্রুটমেন্ট অফ গুড টিচার্স। বিশেষ করে এই মুহূর্তে আমরা তো বুঝতেই পারলাম কি হয়েছে গত কয়েক বছর, ঠিক আছে? আমি কোনো পলিটিক্যাল সাইডে যাচ্ছি না, বাট প্রপার রিক্রুটমেন্ট অফ গুড টিচার ইজ ভেরি ভেরি ইম্পর্টেন্ট। একটা এডুকেশন সিস্টেমকে গুড টিচার্সরাই একমাত্র এগিয়ে নিয়ে যেতে পারেন। তারপরে, কারণ গুড টিচার থেকে গুড স্টুডেন্ট তৈরি হবে, গুড স্টুডেন্টরা পরে গুড টিচার হবে। কিন্তু যদি টিচার ব্যাড হয়, তারা গুড স্টুডেন্ট করতে পারবে না, কারণ এটা এক্সটেন্টটা সাধারণভাবে কমে যাবে, ইত্যাদি ইত্যাদি। যেটা বললাম যে এডুকেশন সিস্টেম একটা সোসাইটিকে নষ্ট করে দেওয়ার পক্ষে, জাস্ট এডুকেশনটাকে নষ্ট করে দেওয়া, সোসাইটি এমনি নষ্ট হয়ে যাবে। কিন্তু এখানে এর আগে তো আমি সব বললাম যে এতগুলো প্রবলেম আছে, রাইট? প্রবলেমস। কিন্তু একটা জিনিস সবাই জানবে, যে যখনই আমি কারোর দিকে এইটা দায়ী ওইটা দায়ী, এই যে আঙুলটা দিচ্ছি, এই 3টে আঙুল কিন্তু আমার দিকে আছে। So whenever you finger at someone, মানে এই রিজন, ওই ব্যক্তি, আমার দারিদ্র বা গরিবি, এসবগুলোর জন্য আমি করতে পারি না স্যার, আমার কারেন্ট থাকে না, যখনই আমি কারোর দিকে আঙুল দেখাচ্ছি 3টে আঙুল আমার দিকে থাকে। So if that be a reason, I am 3 times more responsible than that reason. এটা সবসময় আমাদের মানতে হবে। দিস ইজ রিয়েলিটি, এটা বাস্তব। যে কেউ এটা প্র্যাকটিস করে দেখতে হবে। আমি যদি আঙুল দেখাই কারোর দিকে, আমার 3টে আঙুল আমার নিজের দিকে, এটা মিনিংফুল আমার কাছে। এবার একটা বলছি, আমার লম্বা এক্সপিরিয়েন্স অফ টিচিং আছে, সেখান থেকে বলছি ফিলিংস অফ দ্য হাই স্কুল স্টুডেন্টস টুয়ার্ডস কেমিস্ট্রি। কেমিস্ট্রিকে হাই স্কুল স্টুডেন্টরা ইন জেনারেল কিভাবে দেখে কেমিস্ট্রিকে? নাম্বার ওয়ান, এ ফ্রাইটেনিং অ্যান্ড ডিফিকাল্ট সাবজেক্ট, একটা ভয়ঙ্কর এবং যথেষ্ট কঠিন সাবজেক্ট। দেয়ার ইজ হার্ডলি এনিথিং দ্যাট ওয়ান ক্যান এনজয় অ্যান্ড প্লে উইথ। খেলাধুলো করার মতো এর মধ্যে কিছু নেই। এ সাবজেক্ট জাস্ট টু মেমোরাইজ। এটা স্কুল লেভেল থেকে এসে যায় তাদের মাথায়, যে কোনোভাবে টিচাররাই রেসপন্সিবল তার জন্য এটা ঢুকিয়ে দেওয়া হয়। কিন্তু আমি ডেমো দিয়ে দেখিয়ে দিতে পারি দিস ইজ নট ট্রু। যেমন একজন ছাত্রকে আমি দুটো এক্সপেরিমেন্ট করছি। এক্সপেরিমেন্ট 1, একটা ছাত্রকে যদি বলা তোমার কতজন বন্ধু আছে, সে সঙ্গে সঙ্গে বলে দেবে 30, 35, 40 জনের নাম বলে দেবে। এছাড়া সে বাবাকে চেনে, মাকে চেনে, অমুক অমুক করে মোটামুটি প্রায় 90 থেকে 100 জনের নাম জানে। শুধু তাই না, ওইদেরকে কাউকে যদি হঠাৎ যদি আমি বলি তোমার বাবা কি করছেন, ওর মনে কিন্তু বাবার মুখটা এসে যায়। তাহলে এই এত জিনিস করেসপন্ডেন্স ওর মধ্যে রয়ে গেছে। যদি জিজ্ঞাসা করি তুমি এগুলো মনে রাখছো কি করে, মুখস্থ করছো প্রত্যেকদিন সকালবেলা আমার নাম অমুক, আমার বাবার নাম না? নিশ্চয়ই না। উত্তরটা ছেলেরা মেয়েরা দেয়, স্যার থেকে যায়। কিন্তু সেই ছেলেটি বা সেই মেয়েটিকে একটা কেমিস্ট্রি সিম্পল প্রশ্ন করো, স্যার মনে নেই, পড়েছিলাম মনে নেই। তাহলে একটা জিনিস এত সহজে মনে থাকছে, আর একটা জিনিস মনে থাকছে না কেন? ডিফারেন্সটা কি, কোথায় গ্যাপ থাকছে? দ্যাট ইজ লাভ, LOVE, ভালোবাসা। আমরা এই যে 100 জনকে ভালোবাসি, আর এই কেমিস্ট্রিটাকে আমরা ততটা ভালোবাসি। দিস ইজ ফ্যাক্টর নাম্বার 1। এবার আমি সেকেন্ড পার্টে সেকেন্ড এক্সপেরিমেন্টে চলে যাই, সেকেন্ড ফ্যাক্টরটার জন্য। সেটা কি, যে ছেলেটি 30 জন বা 40 জন বন্ধুর নাম বলে দিল, তাকেই আমি যদি বলি, সেই সেম ব্যক্তিকে আমি যদি বলি যে তুমি যখন ক্লাস 1-এ ছিলে তখনকার বন্ধুদের নাম বলো, তখন 1, 2, 3, 4, 5 বড় জোর, তারপরে হবে না। কেন? একই তো লোক, একই ছেলে বা একই মেয়ে। কারণটা হচ্ছে ওই মাধ্যমিকের পরে প্রাইমারির পরে ক্লাস 1-এর পরে এতটা আস্তে আস্তে তারা সব বিভিন্ন জায়গাতে ছড়িয়ে গেছে। তারপর তাদের সঙ্গে সামাও কোনো যোগাযোগ নেই, চর্চা নেই, রিক্যাপিচুলেশন নেই এই ভালোবাসা সাবজেক্টের প্রতি। এবং যদি এক সার্টেন টাইমস রিক্যাপিচুলেট করো, তাহলে তোমাকে কোনো কিছু মুখস্থ করতে হবে না, থেকে যাবে। ঠিক যেরকম বাবার নাম মায়ের নাম থেকে যায়, সেরকম থেকে যাবে। ভালোবাসতে হবে নাম্বার 1, সেকেন্ড হচ্ছে রিক্যাপিচুলেট করতে হবে কিছু সময় অন্তর অন্তর। এবার কেমিস্ট্রিটা এত ভয়ঙ্কর ওদের কাছে, দেখা যাক কেমিস্ট্রির বিউটিটা কি। পেট্রোল আমরা জানি হাইলি ইনফ্লেমেবল, আর জল ফায়ার এক্সটিংগুইশার। আমরা জানি দমকলের জলটাই মূলত ব্যবহার করা হয়, সবসময় না, মূলত। এইবার আমরা সোডিয়াম একটা মেটাল আছে, তোমরা সবাই জানো, পেট্রোলের মধ্যে আমি ঢেলে দিলাম, কি হবে? একটা কন্টেনারে পেট্রোল আছে, আমি সোডিয়াম দিয়ে দিলাম, কিচ্ছু হবে না, সেফ থেকে যাবে। আচ্ছা, বাই দি ওয়ে, আমরা কখন এটা শেষ হবে, শেষ হওয়ার কথা? Can you please tell?
হ্যাঁ, এটা আমরা
12:25, হ্যাঁ, 12:30, হ্যাঁ 25 স্যার।
ঠিক আছে, থ্যাংক ইউ। আচ্ছা, সোডিয়াম যদি আমরা পেট্রোল, একটা কন্টেনারের মধ্যে পেট্রোল হচ্ছে, সোডিয়ামটা কি কিচ্ছু হবে না, নাথিং হ্যাপেন্স। কিন্তু পেট্রোল ইজ হাইলি ইনফ্লেমেবল, রাইট? এবার আমি সেই সোডিয়ামটাকে যদি একটা কন্টেনারে ওয়াটার রেখে তার মধ্যে দিই, সঙ্গে সঙ্গে একটা ফায়ার হবে এবং এক্সপ্লোশন হবে। তাহলে এটা কি এখানকার জাস্ট অপোজিট হলো না? পেট্রোল হাইলি ইনফ্লেমেবল, ওয়াটার ফায়ার এক্সটিংগুইশার, অর্থাৎ আগুন ধরে না, অথচ যখন আমি সোডিয়ামটা জলের মধ্যে দিলাম আগুন ধরে গেল। একটা ফ্যালাসিয়াস সিচুয়েশন। ফ্যালাসির অরিজিন কি? কখন ফ্যালাসি তৈরি হয়? ফ্যালাসি কামস ফ্রম ল্যাক অফ আন্ডারস্ট্যান্ডিং অর গ্যাপ ইন নলেজ। কোথাও একটা গ্যাপ আছে। আসলে এক্সপ্লেনেশনটা সবাই জানো, তাও বলে দিচ্ছি। পেট্রোলের মধ্যে সোডিয়াম দিলে কোনো রিয়াকশন হয় না, কোনো কেমিক্যাল রিয়াকশন হয় না, যার ফলে ওটা সেফ। কিন্তু যেই আমি ওয়াটারের মধ্যে সোডিয়াম ফেলে দিলাম, সোডিয়াম প্লাস ওয়াটার, সোডিয়াম হাইড্রোক্সাইড প্লাস হাইড্রোজেন, এই হাইড্রোজেনটা এক্সট্রিমলি হাইলি ইনফ্লেমেবল, পেট্রোলের থেকে অনেক বেশি। কিন্তু যে কোনো জিনিসে আগুন লাগতে গেলে তার ইগনিশন টেম্পারেচার বা ইগনিশন পয়েন্টের উপরে টেম্পারেচার আনতে হবে। তাহলে সেই হিটটা পাচ্ছে কোথা থেকে? এই যে রিয়াকশনটা সোডিয়াম প্লাস ওয়াটার থেকে সোডিয়াম হাইড্রোক্সাইড হাইড্রোজেন, এটা এক্সোথার্মিক রিয়াকশন, তাপ উৎপাদক এক্সোথার্মিক রিয়াকশন। So it produces heat, and that heat raises the temperature to above the ignition temperature of hydrogen. So actually what is burning there is not water, it is only hydrogen gas that is burning. Okay, so যদি আমি নলেজটা আমার থাকে তাহলে কিন্তু আমি বলবো ও এটা নর্মাল জিনিস, ফায়ার এক্সটিংগুইশার হলেও ওয়াটার তো বার্ন করছে না, ওয়াটার বার্ন করতে পারে না, তা হাইড্রোজেন বার্ন করছে, রাইট? আচ্ছা, আমি এরকম কতগুলো এক্সাম্পল দিচ্ছি। A citable signs of ancient India, পুরনো ইন্ডিয়াতেই অনেক মানে আগে আদিকালের সময়ে অনেক সায়েন্স ছিল। এটা কি অনেকেই জানতে পারেন বা জানতে পারো, এটা হচ্ছে কি আয়রন পিলার নেক্সট টু কুতুব মিনার, দিল্লিতে কুতুব মিনারের পাশেই যেটা। আচ্ছা, আমরা একটা জিনিস অ্যাটিটিউড দিয়ে শুরু করেছিলাম। এখানে যে ছবি দুটো রয়েছে এটা হচ্ছে আমি, ফরচুনেটলি আর আনফরচুনেটলি, আর আমার মিসেস। এটা অনেক আগে, আমরা এটা সম্ভবত 2001 সালের তোলা ছবিটা। তখন কিন্তু জাস্ট টুরিস্ট হিসেবে তুলেছিলাম, কিন্তু যখনই আমি টিচ করতে যাচ্ছি, অর্থাৎ আমি কিছু লেকচার দিতে যাচ্ছি, তখন আমার মনে হয় আরে ওইটার মধ্যে সায়েন্স ছিল। দিস ইজ অ্যাটিটিউড। Please try to develop this sort of attitude. I'm not boasting of myself, no, not at all. Please don't think that way. But আমি বলছি যে অ্যাটিটিউডটাই কিন্তু আমাকে এই ছবিটাকে এখানে নিয়ে এসেছে। যদিও এই ছবিটা তোলার সময় আমি জানতাম না, জাস্ট একটা টুরিস্ট পারপাজে তুলেছিলাম। আচ্ছা, এইটা তার ডাইমেনশন, এগুলো ইন্টারনেটে পাওয়া যাবে। No, what is the speciality of this iron pillar? ফার্স্ট অফ অল, এটা কি সত্যি আয়রন পিলার আমি বুঝবো কি করে? খুব সহজ, পকেটে করে একটা ম্যাগনেট নিয়ে যাব, ওখানে লাগিয়ে দেবো। যদি দেখি যে ওটা হ্যাঁ ম্যাগনেটে আটকে গেছে, ম্যাগনেটটাকে ধরে রেখেছে, তাহলে ওকে, দিস মে বি আয়রন পিলার, ফাইন। তাহলে আয়রন যদি হয়, আমি একটা চকচকে লোহার নেল বা পেরেক বা স্ক্রু কিনলাম দোকান থেকে, চকচকে, ফাইন, আমি আমার বাড়ির উঠোনে রেখে দিলাম। এক সপ্তাহ পরে কি দেখবো? এখন তার বর্ষাকালে তো হলে আরো ব্যাপার, আরো ভালো ব্যাপার, ওটা রাস্ট করে যাবে। 1 মাস পরে ও থাকবেই না, টুকরো টুকরো হয়ে পড়ে যাবে, কিছু পাবোই না, ওই টুকরো টুকরো গুলো পাবো, রাস্ট পড়ে গেছে। কিন্তু এইটা খোলা জায়গাতে আছে, জল পাচ্ছে, রোদ পাচ্ছে, অক্সিজেন, নাইট্রোজেন সবই পাচ্ছে, কার্বন ডাই অক্সাইড সবই পাচ্ছে, তাহলে এটাতে কেন রাস্ট পড়ছে না? ওইদিকে এটা আয়রন পিলার, আয়রন আমি সত্যি ম্যাগনেট দিয়ে দেখলাম, হ্যাঁ সত্যি এটা আয়রন, তাহলে কেন হচ্ছে না? এটা কিন্তু চোখের সামনে সবার আছে। অ্যাকচুয়ালি এইখান থেকে আমরা মেটেরিয়াল সায়েন্সে ইন্টারেস্টটা গ্রো করতে পারি, ডেভেলপ করতে পারি। এবং আমাদের টিচারদের রেসপন্সিবিলিটি হচ্ছে এইটুকু, যে তোমার চোখের সামনে ওইটা আছে, তুমি দেখতে গেছিলে, সায়েন্স ওইখানে আছে। এবার আমরা বুঝবো কি করি যে ওটাতে এর বিশেষত্ব হচ্ছে নো রাস্ট। এবার এটা কি কিভাবে বুঝলাম? আমরা যদি এর মেটেরিয়ালটা ডেনসিটি মাপি, ডেনসিটিটা দেখা যায় 7.81 গ্রাম পার মিলিলিটার। এই যে কন্টেন্ট অফ দিস পিলার, তার ডেনসিটি হচ্ছে 7.81 গ্রাম পার মিলিলিটার। কিন্তু পিওর 100% পিওর আয়রন, তার ডেনসিটি হচ্ছে 7.84 গ্রাম পার মিলিলিটার। তাহলে খুব সহজ ব্যাপার, একটা ম্যাগনেট নিয়ে যাও, দিয়ে দেখো এখানে এটা আয়রন কিনা, হ্যাঁ ঠিক আছে, আটকে গেছে, আয়রন হতে পারে। এবার এটা ডেনসিটি মাপবো, আমি ওখান থেকে একটু স্ক্র্যাচ করে নিলাম, নিয়ে ডেনসিটি মাপতে পারি, অনেক মেথড আছে। তা ডেনসিটি যদি এইটা হয় তাহলে ওটা পিওর আয়রন, কিন্তু দেখা গেল যে না, ওটা ডেনসিটি এইটা। তবে আমি যে সেকেন্ড পার্টটা বললাম, ম্যাগনেট নিয়ে তুমি এটা টেস্ট করতেই পারো, কিন্তু সেকেন্ড পার্টটা করো না। এই একটু একটু করে স্ক্র্যাচ করে নাও। আমাদের 130 কোটি দেশ, 1 সপ্তাহের মধ্যে দ্যাট উইল বি গান, ভ্যানিশ হয়ে যাবে, সেটা কখনোই অ্যাডভাইসেবল নয়। তাহলে এই যে সামান্য একটু কম ডেনসিটি, এখানেই সায়েন্স। তাহলে আমাদের কনক্লুশন কি করতে হবে? দিস ইজ নট মেড আপ অফ অনলি আয়রন, পিওর আয়রন এটা নয়। যদি পিওর আয়রন থেকে হতো তাহলে এখানেও রাস্ট পড়ে যেত, এটা এতদিন সার্ভাইভ করতো না, ঠিক করতো। এরপরে আমরা ডিটেল অ্যানালিসিস করছি, ডিটেল কম্পোজিশন করলাম, তাতে দেখলাম যে হ্যাঁ 99.7% আয়রন। তাহলে তো আমি রাফলি বলবো আয়রন পিলার না, 99.7, বাট there are some other things like this so many things. That is not important. But important is, if you just if you can introduce some other external agents in judicious way, then you can tune the property of the material dramatically. Okay, so that is a very simple and catchy example to put emphasis on material science. এখান থেকে শেখা উচিত what is importance of material science. আমরা স্টিলের থালাবাটি যে ব্যবহার করি আসলে তো আয়রন, কিন্তু তার মধ্যে বিভিন্ন রকম আছে, কার্বন আছে, নিকেল আছে, ইত্যাদি ইত্যাদি, সুন্দর থাকে। আচ্ছা, আমি কতগুলো ছোট্ট ছোট্ট জিনিস দিয়ে বোঝাবো যেগুলো অলরেডি সকলের জানা, কিন্তু কি হাউ টু লার্ন, আমাদের কোথায় গ্যাপ ছিল, আমাদের অনেক জায়গাতে প্রশ্ন করা উচিত ছিল, আমরা করি সেইগুলো দেখি। স্টেটস অফ ম্যাটার, হাউ মেনি স্টেটস অফ ম্যাটার? 3, সলিড, লিকুইড, গ্যাস। এখনকার ছেলেপুলেরা আবার বলে সে প্লাজমা ব্লা ব্লা ব্লা, দরকার নেই, আমি সিম্পল মানুষ, আমার লাইফটাকে সিম্পল করলেই ভালো আছে, কিন্তু যেটুকু সিম্পল জিনিসটা জানবো সলিড জানবো। সলিড, লিকুইড, গ্যাস, একে সলিড দিলাম, হিট দিলাম, লিকুইড হবে, হিট দিলাম, গ্যাস হবে। 3 স্টেটস অফ ম্যাটার। আমরা কি কখনো প্রশ্ন করেছি এটা? হোয়াট হ্যাপেন্স টু ন্যাপথলিন এন্ড ক্যাম্ফর? আমরা তো সবাই দেখেছি ন্যাপথলিন, প্রতিটা ইচ এন্ড এভরি স্টুডেন্ট হ্যাজ সিন ন্যাপথলিন। ন্যাপথলিন সলিড দেখেছে, ন্যাপথলিন গ্যাস দেখেছে, কারণ স্মেল বুঝিয়ে দেয় হ্যাঁ ন্যাপথলিন আছে। হোয়ার ইজ দ্য লিকুইড স্টেট? So the student should ask the teacher, স্যার আপনি বললেন যে 3টে স্টেটস অফ ম্যাটার আছে, সলিড, লিকুইড, গ্যাস, ন্যাপথলিনের তো নেই, কর্পূরের তো নেই। কর্পূর হয়তো সবাই দেখেনি, কিন্তু ন্যাপথলিন তো অবশ্য সবাই দেখেছে, কেন প্রশ্ন করেনি? এখন প্রশ্ন হচ্ছে যে তাহলে এই যে দেয়ার আর 3 স্টেটস অফ ম্যাটার, কোট আন কোট, ইজ ইট এ সায়েন্টিফিক স্টেটমেন্ট? যদি সায়েন্টিফিক স্টেটমেন্ট হয় তাহলে সবসময় ভ্যালিড হবে, অর নট। কিন্তু আমরা এখানে দেখছি ন্যাপথলিনের লিকুইড স্টেট নেই, কোনখানে? একটা ফ্যালাসিয়ার সিচুয়েশন। আবার ফ্যালাসি কোথা থেকে হয়? আগেই বলেছি, ল্যাক অফ আন্ডারস্ট্যান্ডিং অথবা গ্যাপ ইন নলেজ। এটা অ্যাকচুয়ালি ওই গ্যাপ ইন নলেজ থেকে আসছে। আসলে স্টেটমেন্টটাতে বলা আছে দেয়ার আর 3 স্টেটস অফ ম্যাটার, আর কোনো কন্ডিশন বলা হয়নি। কখনো ওই স্টেটমেন্টের মধ্যে বলা হয়নি ইউ উইল বি এবল টু সি অল দ্য 3 স্টেটস অর 3 ফেজেস অ্যাট দ্য সেম কন্ডিশন, সেটা বলা হয়নি। কিন্তু সুতরাং নর্মাল কন্ডিশনে রুম টেম্পারেচার এবং নর্মাল প্রেসার মানে 1 atmosphere প্রেসার, এই কন্ডিশনে ন্যাপথলিনকে আমরা লিকুইড পেতে পারি না। তাহলে আমরা কি করে বুঝবো যে লিকুইড স্টেটটা আছে আদৌ? সলিড আর গ্যাস তো সহজে বুঝতে পারছি, খুব সহজ। একটা টেস্ট টিউবের মধ্যে ন্যাপথলিন সলিড রেখে একটা কর্কের মধ্যে দিয়ে একটা এক্সস্ট পাম্প লাগিয়ে দাও। এক্সস্ট পাম্প পাবো কি করে? স্যার বাড়িতে তো নেই, আপনি বড় বড় সব ফর্মুলা দিচ্ছেন। না না, 3 ইডিয়টস আমাদেরকে গাইড করেছেন। আমাদের অনেকের বাড়িতেই, বিশেষ করে মেয়েদের, এই হেয়ার ড্রায়ার থাকে না, হেয়ার ড্রায়ারে হিটিং পার্টটা বাদ দিয়ে দাও, তাহলে একদিক দিয়ে তো ব্লো করছে, হাওয়া ব্লো করছে কোথা থেকে? একটা মুখ থেকে। তাহলে সেটা সম্ভব হচ্ছে কি করে? নিশ্চয় অন্য মুখ থেকে টানছে। তাহলে আমি যদি এই মুখটা না ইউজ করি, এই মুখটা ইউজ করি, এটা কিন্তু সাকশন পাম্প হিসাবে ব্যবহার করতে পারি, রাইট? 3 ইডিয়টস আমাদের এগুলো শিখিয়েছে। তাহলে যাই হোক, সাকশন পাম্প হিসাবে আমরা একটুখানি প্রেশার লো করতে হবে, আর একটু জল গরম করি, 60-65 ডিগ্রি হলেই হয়ে যাবে। তার মধ্যে যদি আমি টিউবটা ধরি তাহলে দেখতে পাবো, চোখে দেখতে পাবো লিকুইড। ওকে, আগে 3 স্টেটস অফ ম্যাটার, ওটা কারেক্ট সেন্টেন্স। তারপর ভিসকোসিটি অফ লিকুইড, অনেক সময় আমরা প্রশ্ন করে থাকি সলিড লিকুইডের ভিসকোসিটি আর গ্যাসের ভিসকোসিটি আছে। হোয়াট ইজ দ্য এফেক্ট অফ টেম্পারেচার? আমি টেম্পারেচার বাড়িয়ে দিলাম, লিকুইড ভিসকোসিটি বাড়ে না কমে, বাড়বে না কমে, এই প্রশ্নটা থাকে। সেটা আমরা মুখস্থ থেকে বলি স্যার বাড়বে, এবার আবার যদি প্রশ্ন করি বাড়বে না স্যার কমবে, খুব কমন ব্যাপার। কিন্তু দেখো সায়েন্সের উত্তর একই থাকা উচিত। আমি হালকা করেই প্রশ্ন করি বা জোরে করেই প্রশ্ন করি, উত্তরটা এক থাকা উচিত, কিন্তু এখানে উত্তরটা চেঞ্জ হয়ে যায়। কেন? ল্যাক অফ কনফিডেন্স। কেন? ল্যাক অফ আন্ডারস্ট্যান্ডিং। মুখস্থ করি, ইনফরমেশন কালেক্ট করেছো, নলেজ নেই, এডুকেশন, তাই? কিন্তু আমরা খুব সহজেই করতে পারি এটা। আমরা বাটারের এক্সাম্পলটা নিয়ে নিই না, বললাম না সায়েন্স বইয়ে থাকে না, ফ্রিজের মধ্যে আছে বাটার, ডিপ ফ্রিজে রেখে দাও, একদম পাথরের মতো শক্ত, একটা ছুরি দিয়ে গাঁথতে পারবে না, কাগজটাকে খুলে ফেলো, র্যাপারটাকে খুলে ফেলো, একটা থালার উপরে জাস্ট প্ল্যান্টিং করে রেখে দাও বাটারটা। প্রথমে ছুরি ঘাঁটতে পারবে না, একটু পরে দেখবে, একটু পরে মানেটা কি? বাইরে থেকে হিট নিচ্ছে, টেম্পারেচারটা উঠছে। সেটাকে আমরা বলছি টেম্পারেচার বাড়ালে লিকুইডের ভিসকোসিটি বাড়বে না কমবে। তখন দেখবে সলিডটার মধ্যে সহজেই ছুরি গেঁথে দেওয়া যাচ্ছে। আরো ওয়েট করো, দেখবে একটা সময় এখান থেকে বাটারটা গলে 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 নিচে পড়বে। তাহলে ফ্লুইডিটি বা ফ্লো বিহেভিয়ার বাড়ছে, আর ফ্লুইডিটি আর ভিসকোসিটি ঠিক রিভার্স। তাহলে যেহেতু ফ্লো বিহেভিয়ার বাড়ছে, তাতে ভিসকোসিটি ডেফিনেটলি কমবে। দ্যাটস ইট। আমাকে আস্তে করে প্রশ্ন করুন, জোরে করে প্রশ্ন করুন, গানের স্বরে বা যে কোনো স্বরে, ধমকের স্বরে প্রশ্ন করুন, আমরা একই উত্তর হবে। একইভাবে আমরা জানি সারফেস টেনশন, ক্যাপিলারি রাইজ মেথড, অ্যাবসলিউট মেথডে কি করা হয়, একটা ক্যাপিলারি টিউবকে জলের মধ্যে ডোবানো হলো, কিছুটা উঠে গেল, আমরা হাইট মাপলাম, ইত্যাদি ইত্যাদি, সেই গামাইকোটা হাফ এইচ রো জি আর তার থেকে পেয়ে গেল ফার্স্ট ক্লাস। এবারে দেয়ার ইজ এ নটি স্টুডেন্ট, আই লাইক নটি স্টুডেন্ট বিকজ দে আর ইন্টেলিজেন্ট। আমি সে বললো যে স্যার একটা আমার কাছে ধারালো ছুরি আছে, আমি এখান দিয়ে ফাটাস করে একটা মেরে কেটে দিলাম, এখান দিয়ে ব্রেক করে দিলাম হাফ ওয়ে। হোয়াট হ্যাপেন্স ইফ দ্য টিউব ইজ ব্রোকেন হাফ ওয়ে? তাহলে কি এরকম ফাউন্টেন হবে? উত্তরটা হলো না। আমরা খুব সহজেই বলতে পারি জাস্ট থার্মোডাইনামিক্স এর বেসিক কনসেপ্ট থেকে যে ওটা ফাউন্টেন হতে পারে না। কেন? যদি ফাউন্টেন হয়, ধরো এরকম জায়গা, আমি এখানে একটা ছোট টারবাইন বসালাম, একটা অল্প পরিমাণ কারেন্ট তৈরি করবে, এখানেও টারবাইন বসালাম, অনেক টারবাইন বসালাম, আর এই কন্টেনারের মধ্যে আমি আরো অনেকগুলো এরকম টিউব বসিয়ে দিলাম, তাহলে টারবাইন থেকে পাওয়ার জেনারেটেড হবে। এবার এইখান থেকে যদি এটা ফাউন্টেন হয়, এটা নন এন্ডিং, কন্টিনিউয়াসলি চলতে থাকবে, তাই তো? তাহলে আমি কিছু করছি না, কোনো খরচ নেই, আমি পাওয়ার নিয়ে এসছি। পারপিচুয়াল মেশিন অফ দ্য ফার্স্ট টাইম হতে পারে না, তাই না? আমাকে তো কিছু পেতে গেলে কিছু খরচ করতে হবে। পিএইচ, এই ডেফিনেশনটা অনেক সময় আমরা বলছি হোয়াট ইজ পিএইচ, ম্যাক্সিমাম ক্ষেত্রে উত্তর পাই স্যার মাইনাস লগ অফ পিএইচ। না, হোয়াট ইজ পিএইচ যে কোনো জিনিসের, যে কোনো টপিকের প্রথম প্রশ্ন হওয়া উচিত হোয়াট ইজ পিএইচ, এবং তাই যদি হয় তার উত্তরটা এমন হওয়া উচিত যাতে বোঝা যায় হোয়াট ইজ দ্যাট থিং। খায় না মাথায় দেয়, খাওয়ার জিনিস না মাথায় পড়ার জিনিস না অন্য কিছু, কি জিনিস সেটা বুঝতে হবে। অ্যাকচুয়াল উত্তরটা হচ্ছে পিএইচ ইজ এ স্কেল। তো ইটস এ স্কেল। যেমন আমি বড় না, তোমাদের স্টুডেন্টদের মধ্যে কেউ একজন বড়, ডেফিনেটলি আমি বড়। কিসের ভিত্তিতে বলছি? টাইম স্কেলে আমি অনেক আগে এসেছিলাম। স্কেল ইন্ডিকেটিং দ্য অ্যাসিডিটি অর বেসিসিটি অফ এ সলিউশন। শুধু তাই না, এটা হাফ। কারণ প্রশ্নটা হলো হয়ে যাবে এরপর, তাহলে কিভাবে? ম্যাথমেটিক্যালি পিএইচ ইজ ডিফাইন্ড অ্যাজ মাইনাস লগ অফ সিএইচ অ্যান্ড দেন সিএইচ ইজ blah blah blah, you know. I think I should end. আমি লাস্টে একটা জিনিসে আসছি, এগুলো হয়তো অনেকেই জানো। হোয়াট ইজ দ্য পিএইচ অফ 10 to the -8 মোলার HCl সলিউশন? যদি আমরা ক্যালকুলেট করি মাইনাস লগ অফ সিএইচ, তাহলে দেখা যাবে 8। সেটা হতে পারে না, কারণ আমরা স্কেলে জানি 8 হচ্ছে বেসিক রিজন। আমি HCl কে ডাইলিউট করছি, সে বেস হয়ে যাবে? হতে পারে না তো কখনো। কিন্তু তাহলে অ্যাকচুয়াল উত্তরটা কি হবে না, অ্যাসিড থেকে যতটা আসছে, আবার জলের ডিসোসিয়েশন থেকে কিছু হাইড্রোজেন আসছে, হ্যাঁ করে আলটিমেটলি 7-এর নিচেই থাকছে, কিন্তু 6.9 7-এর খুব কাছাকাছি। নাও দ্য কোশ্চেন ইজ হাউ টু প্রিপেয়ার 10-8 মোলার HCl সলিউশন ফ্রম গিভেন 10 মোলার HCl। তোমাকে ল্যাবরেটরিতে নিয়ে যাওয়া হলো, সব জিনিস তোমার কাছে আছে, 10 মোলার HCl দেওয়া আছে, এবার বলা হলো 10 to the -8 মোলার HCl বানাও। কিভাবে বানাবে? স্যার সহজ ব্যাপার, V1S1 = V2S2 অঙ্ক করো, দেখা গেল যদি আমি 1 মিলিলিটার 10 মোলার HCl নিই, তাহলে যে ভলিউম অফ সলিউশন হবে আলটিমেটলি এটা হচ্ছে 10 to the power 9 মিলিলিটার। তার মানে 10 to the power 6 লিটার। 10 to the power 6 মানে 1 মিলিয়ন লিটার। তার মানে হচ্ছে আমাদের এই কর্পোরেশনের উপরে যে ওভারহেড ট্যাঙ্ক গুলো থাকে তাদের ভলিউম। ল্যাবের মধ্যে আমি কিভাবে তৈরি করব 10 to the -8 মোলার HCl? আমি তো ওই ট্যাঙ্কের মতো ভলিউম ল্যাবে ঢোকাতেই পারবো না, আমরা ওই কন্টেনার নেই। এইখানটাতে প্রবলেমটা কি হচ্ছে, তোমাকে বলা হয়েছে হাউ টু প্রিপেয়ার দিস, আমরা একটা সেলফ ইম্পোজড রেস্ট্রিকশন এনে দিয়েছি, নিয়ে এসছি নিজেরা আননেসেসারি। আমরা ভেবেছি একবারেই করতে হবে, সেই জন্য V1S1 = V2S2 ইউজ করেছি। কে বলেছে? তুমি এক কাজ করো, 10 মোলার থেকে 1 মোলার করো, 1 মোলার থেকে 0.1 মোলার করো, and so on, you will reach there। এবং সবগুলো তোমার 10 মিলিলিটার করে করেই লাগবে। একটাতে 1 মিলিলিটার থেকে 10 মিলিলিটার করো, তারপর আবার ওখান থেকে 1 মিলিলিটার নাও, নিয়ে আবার 10 মিলিলিটার করো, তো সব টেস্ট টিউবের মধ্যে হয়ে যাবে। ওকে, Now, so what is the message? Messages to impart to students. Number one, chemistry is the most applied science. There is no doubt about it. Chemistry is not a subject just to memorize. I mean, bole diyechi, demo diye diyechi. Do not just read science, realize it and play with it. Play jokes with science. Jokes তো এখন হয়তো বলার সময় নেই, যদি তোমরা অ্যালাউ করো পরে আমি বলবো। এটা নিজের জোক বানাও সায়েন্স দিয়ে, ভালোবাসো সাবজেক্ট, ask questions to yourself. Try to apply science to your daily life and enjoy it. That is important. এইবারে an appeal to the teachers from the students. আমি একটা স্কুলে এই কোটেশনটা পেয়েছিলাম, আমার ভীষণ ভালো লেগেছিল, একবার মতো পড়েছিলাম, এতটা ভালোবেসেছিলাম ওটা আমার মেমোরিতে রয়ে গেছে। I did not memorize it. If I can't understand the way you teach, why can't you teach in a way I understand? আমি রিপিট করছি, if I can't, I am a student, if I can't understand the way you teach, why can't you teach in a way I understand? সেই জন্য আমি প্রথমে দিকে বলেছিলাম to read the face of the student, তাহলেই বোঝা যাবে ওরা বুঝছে কিনা, সেই মতো টিউন করা উচিত। আচ্ছা, এইটা শেষ হলো। এইখানে একটা লাস্ট পিকচার আমি দিয়ে রাখি, এটা খেয়াল করে দেখো, আমি ছাত্রদের উদ্দেশ্যে তুমি করে বলছি। এখানে কিছু নেই, এখানে একটা মাছের হালকা শেপ আছে, এইভাবে যদি আমরা যাই পরপর এইটা একটা মাছে পরিণত হয়ে যাবে। আবার এই গ্যাপটা থেকে যদি আমি তাকাই দেখবো আস্তে 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 পাখিটা হয়ে গেল। অর্থাৎ সেই সেম জিনিসটার মধ্যে অ্যাটিটিউডটা তোমাকে ঠিক করে দেবে যে তুমি মাছ দেখবে না পাখি দেখবে। ওকে, থ্যাংক ইউ।
Thank you, Professor Nitin Chattopadhyay, for your illuminating lecture. Now we will start our question answer session. I will request all of you to introduce yourself and put forward your question. Our respected speaker will be quite happy to answer them.
Oh yes, of course.
Does anyone have any question? Please come.
Yeah, if this is what I just said. The ability or attitude of questioning has decreased exponentially and now almost nil. Almost. Let's see if there is any question.
Hello.
Hello.
Hello. Hello.
Yes, I can hear.
হ্যাঁ সংকোদা শোনা যাচ্ছে।
Thank you, sir, for delivering a nice lecture and illuminating lecture. Sir, we are crossing 75 years of independence.
Right.
But at the present scenario, I think that the very minimum number of students are coming in the science stream.
Yes.
What kinds of problem or what are the problems you can suggest or you can weigh out so that the number of students can increase in science stream?
Yeah, that is very relevant question. There is no doubt that science is the most effective or useful subject, no doubt about it, for the prosperity of any country or any state, any province, whatever it may be. Science is essential. But the thing is, as I said, when you just point at something, three fingers point at you, so I always try to blame myself. So it is, as I feel, this is the responsibility of the teachers. I suppose, I think, I believe that the school education is not going in a proper way. So that the science is being presented to the students as a subject of, as a horrible subject. So they try to keep themselves away from science. So unless and until we can change ourselves, we can change our mode of education, mode of teaching. And to do that, we have to change our own attitude first. Unless we can do that, this is impossible. You cannot draw or pull the students to science. That is my understanding.
Sir, I like to share with you, is there any effect of syllabus or infrastructure or laboratory arrangement in the Madhyamik level or HSC level or more emphasis on practical discussion?
Those things are minor. Those things, definitely they have small contributions. But there cannot be only a single reason, not at all. So they all of them have certain amount of contribution, but definitely the most important one is the level of and quality of and ability of teachers.
You see that there is huge difference in syllabus in the Madhyamik and HS levels of science. This may be any problem
It doesn't matter too much, because if a student is যেটা বললাম যদি এডিক্টেড হয়ে যায়, পজিটিভ সেন্সে বলছি, যদি নেশা ধরিয়ে দিতে পারি, যতই কঠিন হোক নিজে সেই গ্যাপটাকে মেকআপ করে দেবে। ও টিচারদের কাছে যাবে যদি ওর নেশাটা ধরানো যায়। আমরা নেশা ধরাতে পারছি না, আমরা একটা পড়াটাকে ওই বই খুললে সায়েন্স আসছে, বই বন্ধ করলে সায়েন্স নেই, এই জায়গাতে আমরা নিয়ে গেছি। সিলেবাস সব পরের ব্যাপার। আমি মানছি যে মাধ্যমিকের থেকে হায়ার সেকেন্ডারি সিলেবাসের বিশাল ডিফারেন্স আছে, কিন্তু সে সব মেকআপ হয়ে যাবে যদি আমরা মাধ্যমিক লেভেলটাকে ভালো করে ওদেরকে সায়েন্স পড়াতে পারি, ওদেরকে সায়েন্সে মোটিভেট করতে পারি। মোটিভেট করতে পারলে তারপর কোনো ফ্যাক্টর না, বাকি সব এক্সকিউজ হয়ে যাবে, ওগুলো সব এক্সকিউজ।
Thank you, sir.
ওয়েলকাম। তোমরা কোনো সিলি প্রশ্ন করতেও পারো, কোনো অসুবিধা নেই, সিলি প্রশ্ন করাটা ভালো। হ্যাঁ, কে বলছেন? হ্যাঁ বলুন। হ্যাঁ, এটা খুব ডিপ কোশ্চেন, একটা গভীর কোশ্চেন। কোশ্চেনটা অ্যাকচুয়ালি হওয়ার কথা, মানে প্রবলেমটা কেন অরিজিনেট করে এই কারণে আমাদের এনর্মাস পপুলেশন, এই পপুলেশনকে কন্ট্রোল করা খুব মুশকিল, এই পপুলেশনকে ওভারঅল ডেভেলপ করানো খুব কঠিন। অ্যাকচুয়ালি কি করা উচিত? প্রত্যেকটা হিউম্যান বিইং এর ইন্ডিভিজুয়াল ক্যাপাসিটি আছে এবং এবিলিটি আছে এবং এক্সেলেন্স আছে। প্রবলেমটা কি হয়, আমরা সবাইকে বলি তোমরা ফিজিক্স, কেমিস্ট্রি, ম্যাথমেটিক্সে ভালো রেজাল্ট করো, দে আর নট বর্ন ফর দ্যাট। কেউ গানের জন্য জন্মেছে, কেউ ফুটবল খেলার জন্য জন্মেছে। আজকে যদি সচিন তেন্ডুলকরকে গান করতে বলা হতো, লতা মঙ্গেশকরকে যদি ক্রিকেট খেলতে দেওয়া হতো, তাহলে কি অবস্থাটা হতো? আমরা সেই যখন এক লাইনে সবাইকে নিতে চাইছি, সবার এক্সেলেন্স নিতে চাইছি, এবং সেখানে যে স্কোরিং হচ্ছে তার ভিত্তিতে ভালো মন্দ মাঝামাঝি এরকম করছি। ঠিক আছে, এটা ঠিক নয়, এটা একদম ঠিক নয়। তবে উপায়টা কি? আমাদের খুব একটা বেশি উপায়ও আছে বলে আমি মনে করি না। আমাদের ক্লাসের মধ্যে 75 জন স্টুডেন্ট আছে, আমরা পাচ্ছি 45 মিনিট সময়। আমি ইন্ডিভিজুয়ালি কার কোন দিকে ন্যাক আছে জানবো কি করে? বিদেশে এটা সম্ভব, কারণ একটা ক্লাসের মধ্যে 12 জন স্টুডেন্ট আছে। একজন টিচারের পক্ষে প্রত্যেক জনকে ইন্ডিভিজুয়ালি মার্ক করা সম্ভব। আমি ইউরোপিয়ান কান্ট্রির কথা বলছি, 12 জন 15 জন স্টুডেন্ট আছে, ওখানে এগুলো খুব সহজ। ও আচ্ছা, তুমি ফুটবলে চলে যাও, আমার ফুটবলের খুব ভালো স্কিল আছে দেখেছি, তাদেরকে আলাদা আলাদা করে দেবে। সেই জন্য একটা ছোট্ট পর্তুগালের মতো দেশ, বেলজিয়ামের মতো দেশ, যেটা আমাদের কলকাতার মতো, পুরো পর্তুগালের পপুলেশন হচ্ছে আমাদের কলকাতার পপুলেশন থেকে কম, অথচ পর্তুগাল একটা ওয়ার্ল্ড টিম দেয়, ওয়ার্ল্ড কাপের টিম। আর আমাদের 135 কোটি নিয়েও আমরা ওয়ার্ল্ড কাপের টিম দিতে পারি না। কারণটা হচ্ছে এইটা, সবাইকে আমরা একই দিকে নিয়ে যাই।
হ্যালো স্যার।
হ্যাঁ,
হ্যালো স্যার, আমি চিরঞ্জিত পাল, রামানন্দ কলেজ থেকে বলছি। স্যার, আমাদের পড়াতে গিয়ে যেটা কিছু জিনিস কাজে লাগে বা স্টুডেন্টদেরকে ফ্যাসিনেট করে, সেটা হলো যে কেমিস্ট্রির যে সায়েন্টিফিক যে আবিষ্কারগুলো, তার কিছু গল্প টল্প সেগুলো যদি পাওয়া যায়, সেই জায়গার কোনো বই কি আমরা জানা আছে? ফিজিক্সের ক্ষেত্রে অনেক পাই, কিন্তু কেমিস্ট্রির যে গল্পগুলো সেগুলো এক জায়গায় কোথাও ভালোভাবে পাওয়ার মতো আমার কাছে কোনো রেফারেন্স নেই। আপনার কাছে যদি থাকে একটু জানান।
না, আমি একদম স্বীকার করছি, ওই যে বলেছিলাম আই ডু নট নো, এটা বলতে হবে। আমি স্বীকার করছি আমার কাছে এই মুহূর্তে নেই, কিন্তু
Okay,
আমি এটাও বিশ্বাস করি আমরা যদি সার্চ করি আমরা নিশ্চয়ই পারবো এটা। আমি এই কানেকশনে বলছি, এটা খুব ইম্পর্টেন্ট পয়েন্ট যেটা চিরঞ্জিত বললেন। আমাদের ফরচুনেটলি আমি প্রফেসর প্রফুল্ল চন্দ্র রক্ষিতের ডাইরেক্ট ছাত্র এবং আই বিলিভ সেকেন্ড মোস্ট ফেভারিট স্টুডেন্ট অফ হিম। উনি বলেছিলেন উনাদের সময় না, ছেলে তখন সায়েন্সটা এতটা ছিল না, উনাদের সময় সায়েন্টিস্টদের লাইফ হিস্ট্রি পড়তে হতো, ওনাদের একটা পেপার ছিল। আর এখন আমরা সায়েন্টিস্টের নামও পড়ার সময় পাই না, সিলেবাসটা এত বেড়ে গেছে, সায়েন্সটা এত এক্সপান্ডেড হয়ে গেছে। এই জন্য এটা মুশকিল, কিন্তু এগুলো দরকার। যে সায়েন্সের যে মজাগুলো, কেমিস্ট্রির মজা, ফিজিক্সের মজা, এই মজাগুলো দিতে গেলে তাদের লাইফ হিস্ট্রি দরকার, কারণ তারা কিন্তু অনেকেই লাইফ হিস্ট্রি থেকে সায়েন্সটা পেয়েছেন। একদম স্বপ্ন থেকে দেখছেন যে বেঞ্জিনটা এরকম ক্লোজ সাইক্লিক হবে, এর আগে সাইক্লিকের কনসেপশন ছিল না, স্বপ্ন থেকে দেখছেন। তাহলে কেমিস্ট্রি কিন্তু স্বপ্ন থেকেও আসতে পারে, এই আইডিয়াটা ছেলেদের দিতে হবে, বাচ্চাদের দিতে হবে। তাহলে এবার আমি আগের প্রশ্নটার সঙ্গে যোগ করে দিই, যদি মাধ্যমিকে এইরকম জিনিসগুলো দেওয়া হয় তাহলে হি উইল বি এডিক্টেড টু সায়েন্স। তাহলে ওই সিলেবাস বেশি কি কম কিচ্ছু এসে যায় না, সব হয়ে যাবে। আমি ভালোবাসলে সব জিনিস আমি করতে পারি।
আমি একটা ইন্টারাপ্ট করে একটা ইনফরমেশন দিচ্ছি যে হ্যাঁ এরকম বই আছে, সেটা হচ্ছে ইন্ডিয়ান কেমিক্যাল সোসাইটি এবারে পাবলিশ করেছে, গল্পের রসায়ন বলে। সেখানে যদিও খুব কম, বাট কিছু ইনফরমেশন অবশ্যই সায়েন্টিফিক ডেভেলপমেন্টের বা স্টোরি হিসাবে দেওয়া আছে।
আমার মনে হয় প্রফেসর চক্রবর্তী ক্যালকাটা ইউনিভার্সিটি, তারও কয়েকটা বই আছে এরকম।
হ্যাঁ, ওনারও বই আছে
পপুলার সায়েন্স লেভেলে। কি হলো না, ভুলে গেছি,
শ্যামল চক্রবর্তী,
ওনারা কতগুলো আছে ছোট লেভেলে, স্কুল লেভেলে। ঠিক আছে,
ঠিক আছে, থ্যাংক ইউ মিস্টার।
ওকে, I think we have to stop this thing because there are
Yes.
other speakers also, no?
Yes, sir. We'll arrange a seminar.
Yeah.
This type of lecture is very exciting for our students also, and they will interact with you directly,
Yes.
and it will be very good for them also. Okay.
I am always dedicated to the students, so
Yes.
there
Yes.
will be no problem. Yeah. Thank you very much. Thank you all.
Yes. Thank you.
Now our question session, answer session has ended. So I request Dr. Anindita Mukherjee to introduce our next speaker. Over to Anindita.
Thank you, madam. Now we will start our second technical session. Our next speaker is Dr. Noeem Sipai from Lady Brabourne College. It's our great pleasure to have Dr. Shankar Prasad De of Behala College with us today. I would like to request Dr. De to chair the next session. Dr. Shankar Prasad De is an associate professor of chemistry, Behala College. He has the experience of teaching in UG level for more than 20 years and PG level for about 16 years. He was the first coordinator of MSc course in chemistry of Diamond Harbour Women University. 2 students working under his supervision have been admitted to PhD degree under Jadavpur University. He has more than 30 research papers published in journals of international reputations. Besides, he has authored 4 books in chemistry also. Now I will request Dr. Shankar Prasad De, please, to introduce our next speaker, Dr. Noeem Sipai. Sir, please.
Thank you, Anindita, for a nice introduction. I would like to convey my sincere thanks to the principal, Dr. Rajyasri Yogi of Vijayagor Jyotish Rai College, and also to all the members of the organizing committee. And I like to express my sincere thanks to Dr. Dasarath Mal for his energetic, enthusiastic and challenging effort for organizing such national and international webinar on a regular basis, which are very much encouraging and enriching ourselves, and also developing the honor of the college and department of chemistry of Vijayagor Jyotish Rai College. It's really a pleasant moment and pleasant opportunity to me, and I feel proud of it to get a chance for introducing Dr. Naeem Sipai. Dr. Naeem Sipai was a PG student. My PG student of Ramakrishna Mission Vivekananda Centenary College, Rohda, a premier institution of our country. After completing his MSc from this institution, Dr. Naeem Sipai has completed his PhD degree from Jadavpur University under the supervision of Professor Ashok Kumar Mullik, and he has also carried out his postdoctoral research work from the same university. Dr. Naeem Sipai has worked as a faculty, guest faculty of Diamond Harbour Women University, and he has also worked as a guest teacher of Jadavpur University for about 4 to 5 years. Dr. Naeem Sipai is working mainly on the area green organic synthesis, protein chemistry, and molecular engineering. He is a growing scientist and challenging researcher. Dr. Sipai has published about 75 research papers in the journal of international repute. Only within 9 years from starting his PhD work, now he is at the age of 32 to 33. I am proud of it because Naeem Sipai was my student. He first published his research work with me in an elite journal, and he has also written a book with me on the topic green chemistry. He has developed many area of chemistry. Now he is going to deliver a lecture on the topic entitled Non-Covalent Interaction-Based Drug Designing. Basically, this area has been developed by Naeem Sipai. I think his lecture will encourage you and you will enjoy his lecture. With this brief introduction, I would like to welcome Dr. Naeem Sipai, a teacher of the Chemistry Department of Lady Brahman College. Please, Naeem Sipai, start your lecture.
Thank you, sir. Thank you for your introduction, a long introduction. And I would like to thank Vijayagarh Jyotish Rai College, especially Principal Ma'am and Dasharatha for inviting me for this, to share my work in front of you. And without wasting my time, your time also, I want to go for our topic. So here, as Sir said, obviously it should be interactive, and then it will be very easy to understand everything. So this, if we try to understand what is drug design is just a method how we can find a drug or supposed to be drug. So for this, we need to know about the cell. So in this picture, we can see a cell. It is the most detailed picture of a cell, which is obviously simulated. So if we see inside the cell, there are a lot of things. So for a disease, obviously one of these protein or things, if they are infected or blocked or they overexpressed, then any disease or any non-function can happen. So if we see, to develop a drug, we have to target one of them. So if we take a simple anatomy of a cell, then we can see it contains a lot of subcellular parts like mitochondria, plasma membrane, and nucleus, say different type of proteins. So these are obviously our target of drug design. So what are the current method to develop one compound or to identify a compound which can act as a drug? So we have, after identification of a target, we have basically broadly two methods. One is ligand-based drug design, another is structure-based drug design. Ligand-based drug design is it is actually started very first and obviously still running now. In this case, we need to know the structure of a compound which have some biological property. So this ligand-based drug design have these four broad classes and these four broad methods how we can develop one drug molecule or we can get a lead molecule. So if we see the ligand structure information, structural information can give one compound which can act as a drug. We can model a pharmacophore model. If we know a series of compound having biological activity, then using this analogy of the structure, we can develop one lead molecule or one potential molecule. We can get this sort of molecule using ligand-based virtual screening. We can develop structure-activity relationship, and it can help to develop one lead molecule. It is very interesting. We do not need know any structure of the target molecule, but we have to know where we need to target or where we like to target. It is a protein or a DNA. We have to know this. And in second part, it is structure-based drug design. Obviously, here we need to know the structure of the target molecule, like protein or DNA. After this, we can use the molecular docking, de novo drug design, pharmacophore modeling, and molecular dynamics, and it can give one lead molecule. And this lead molecule, if this lead molecule can act as a drug, then we can get the drug candidate. If not, then we have to rethink from the beginning. So if we try to understand the ligand-based drug design, where is the most important challenge and how they function? So for this, we have to get, or we have to have one chemical space or a very large database of compound having particular activity or particular inhibition activity or particular activity of a for a disease. So after that, we need a expert. He is very important person because he have the knowledge to identify which molecule are basically most important for his drug design. So after his this selection, we can get a training set and a testing set. So using these two sets, we can get a model of molecule. Then this model can be fit with the active molecules, and then we can get our best molecule or lead molecule. And as I say, we do not need to know any structure of the protein or DNA for this process. But in case of structure-based drug design, then we need to know the structure of the protein or DNA or our target. So for this, we have to get the knowledge of the gene or which gene is involved or which protein is involved for this purpose or for this disease. After that, we have to collect this protein or the target. Then we have to get a crystal. Then it should be good crystal. Then we have to get a X-ray diffraction. Then after the solving this distraction, we can get the protein structure. We can get this protein structure from the NMR technique or cryo-TEM technique, neutron diffraction technique, or homology modeling. In this way, if I get the structure, then we can use our compound database. And this compound database, whatever it may be active or not, or whether it is tested for this molecule or not, doesn't matter. If we have a database of compound, then we can take this molecule and try to fit the molecule inside the active site of the protein. And before this, we have to find the active site of the protein. If we know the structure of the protein, then it is very simple to identify the active site. Then the best molecule which can fit inside the active site, it can be a lead molecule. Then if we use or synthesize this molecule for experimentally, and we can get the result, on the basis of this result, we can get the lead compound. So when a protein crystallizes, sometimes it crystallizes with a small molecule like this. Protein is very, very large molecule. So in presence of small molecule, their crystallization sometimes favors. Then how this small molecule bind at this center, not this center or this center? So the answer is the non-covalent interactions. These type of interactions actually give a direction where this molecule can bind or not. And obviously the shape of the active site also determine or also indicate this binding. Now, what are the non-covalent interactions? Actually, if we try to classify, then we can get these 4 broad classes. One is electrostatic, another is pi stacking interactions, van der Waals interactions, and hydrophobic interactions. Like electrostatic interactions, it actually confined to ionic interaction, hydrogen bonding, and halogen bonding. Then pi stacking interactions is pi stacking, pi ion, which may be pi cation, pi anion, and polar pi interactions. Van der Waals interactions actually dipole-dipole interaction, ion-dipole interaction, and induced dipole interactions, and hydrophobic interactions. These interactions are very important for protein structure and their interaction with small molecules. If we try to understand what is ionic interaction, when sodium throws its electron to chlorine, then we can get sodium ion and chloride ion, and this interaction is electrostatic interaction or attraction of 2 charges. In case of protein, we can see it contains carboxylic acid, aspartic acid, and arginine, and these 2 amino acids can interact with each other through electrostatic interaction, attraction, minus charge and plus charge. Like lysine and aspartic acid, in the same way it can interact with ionic interaction. Another thing is hydrogen bonding. Hydrogen bonding, in first or early times, we know, or our understanding was that it was a electrostatic interaction type, but now a series of work can show it is a interaction of some orbitals. So if we consider this amide, then this amide can have 2 lone pairs, one this and another is this type, and this is NH bond. So anti-bonding of NH bond is accepting the lone pair of this ketone is one kind of hydrogen bonding. So it is actually donation of lone pair to the sigma bond. So this sort of interaction is actually hydrogen bonding, and it is a very interesting hydrogen bonding type where the NH bond is NH sigma bond pi star is accepting the lone pair of NP of the amide. So another kind of interaction can possible, that is CH bond this is CH bond, not a polar bond, but it can, the sigma star of the CH bond can accept electron or lone pair of electrons from the carbonyl, and this interaction is called non-classical hydrogen bonding. And these hydrogen bondings or these interactions is very important for the structural stability of protein. And it is halogen bonding, where CBr bond, the antibonding of CBr bond can accept electron from a anion or electron rich system, and it can be seen in the protein. And obviously all these interactions are very crucial for stabilizing the structure of the protein and protein structure interactions. And for pi stacking, these four are main pi stacking interactions, which is sandwich, obviously parallelly replaced, and it is the T-shaped, Y-shaped. T-shaped is most stable or most stable pi stacking interactions, but it is obviously lower in stability. And in case of pi cation, this series a pi cation interaction where a benzene ring is interact with a cation, and we can see this sort of interaction in our UG classes. If you take naphthalene or anthracene and give silver chloride, silver ion, then you can get a black PPT, and this is actually for this sort of pi complex. And this is very crucial interaction inside the protein, where this sort of amino acid having NH3, it can interact with the benzene ring. And obviously if you put a small molecule inside a protein, there may be a chance of this sort of pi anion or cation pi interaction. Similarly, anion can interact also with the benzene ring pi systems, and you can see here the benzene ring is interacting with the acid group. So, and another important and interesting type interaction is polar pi interaction. All we know the fact of azeotrope, where hydrophobic benzene interact with water. So this sort of interaction can possible for this sort of azeotrope formation can possible for this sort of interaction. And polar pi type interaction is CH pi interaction. This sort of all these interactions obviously stabilize the complex of small molecule and protein, as well as the structural stability of the protein. And dipole-dipole interaction, where two ketone or amide of the protein can interact, have the dipole moments. You can see here it is delta plus and delta minus, and these two pole and another such kind of pole can interact with each other to stabilize the structure. And now it is most important, it is ion dipole interaction, when one in case of metal enzyme or it is a potassium ion, and we can see 4 units of a protein can interact with each other through a potassium ion, and it can form a quaternary structure like hemoglobin like structure. So this sort of ion dipole interaction is very important for protein structure. And here a sulfate ion, and it is most important for this protein. We can get this sort of loop, and it is very stabilized loop. We can see this sort of bend in every structure of the protein. So ultimately we find here it is a potassium ion which stabilize this loop due to this ion dipole interaction, and it is induced dipole interaction, where if there is dipole which can induce a molecule having no poles, after interaction it can stabilize like this. And another most important interaction is hydrophobic effect. What is it? If we see these two part and these two fragment, and these two fragment is hydrated with water, and now if they combine with each other, then a lot of water can remove from this junction, and this elimination of water actually stabilize this system entropically, because a lot of entropy can gain after the joining by the system. And this interaction is called hydrophobic interaction, and this hydrophobic interaction actually very important for stability of the protein structure. Why? If you consider this peptide chain, and each peptide chain contain a lot of hydrophobic groups or hydrophobic side chains of amino acid, and now if they combine like this, then a lot of water can remove, which is actually hydrated these groups. Then it can entropically drive this structure, the formation of this structure, and this protein folding is stabilized by it, this effect. Okay, so as I say, or as we see earlier, here the interaction of small molecule with the protein actually can possible through this sort of interactions, and our interaction knowledge can help to design this molecule. How? For this work, we choose this protein. It is called M-Pro or M-protease, main protease. It is an enzyme of coronavirus or any other type of virus. Or multiple type of virus can contain this protein. It is very important protein for them. If we get this protein structure and we consider for this study 128 structures, and if we overlay all these structures with each other, then we can find this sort of image where we can see at a place where a lot of small molecules are there, and some small molecules are spread over the protein, throughout the protein. So if we consider this place, actually it is the active site of the protein. So if we eliminate all these molecules which is spread over the molecule, they are bind at other site than active site, and we can get, obviously we found that there are 9 such proteins having no small molecules which is attached before in the time of crystallization. So we get 23 such molecules having small molecules outside the active site. So here 69 such protein structure is available which have the small molecule at the active site bound covalently. There is a covalent bond between this protein and the small molecule, and 27 molecules, such molecule is present which have no covalent bond at all. So if we analyze the active site, then we can find there are 4 domains: S1 prime, S1, S2 and S4. And this S1 actually contain one cysteine unit C145 which can attack, which actually this SH group can use for the protein hydrolysis. Okay, so this SH can attack our designed molecule like this, and it can help to bind this small molecule with covalent bond. So this structural information, actually investigation of this active site, we can get this very important information. Now if we look at the distribution of molecules, we can find it, the covalently bound, all the covalently bound molecules are attached here. At the S1, their density is high in S1 prime and S1 region. And if we see, the non-covalently bound molecules are actually concentrated in this region, S2 and S4. Okay, so what is the reason for this selectivity? After that, we consider all the small molecules and find this, what functional group is most populated in these small molecules or all these small molecules. Then we find this alpha chloro or alpha haloamide is highly populated. It is 65% of the total molecules. So if we want to design one molecule, it should contain one alpha chloroamide. So it is most suitable functional group for this molecule. Now, if we investigate all the amino acids present in the at least 1% of the interaction in this active site with the small molecules, then we can find these amino acids, and we can see H41 having the highest interaction, then C145, then we can see M49, and so on. We can arrange them in this way. Okay, it is very interesting to note that if we all these amino acids, if we consider all these amino acids, are they very significant in the in terms of interaction? Then we perform actually the Poisson distribution to identify which amino acids are significant for interaction with the small molecules. Then we find these amino acids, and then we try to understand what is the nature of interactions which is involved in the small molecule and protein interaction. If we consider the H41, we can see it prefer to interact with aromatic molecules. So we can get the 16% of total interactions is aromatic, and we can find polar is very low, more than 2%, and below the 2% is hydrogen bonding. So M49, it also prefer to interact aromatic interactions. So in this region, if we place one aromatic group, then their interaction obviously more favorable, because these amino acids want to interact with aromatic compounds or aromatic moieties. Like obviously M49 also like to interact with the small molecule through aromatic interactions, like pi stacking interactions, CH-pi interactions. So this information can help us to design a molecule with better activity. So it is very interesting. These two amino acids obviously very important, and we can see glycine 143 interact only through hydrogen bonding, and cysteine, it also interact through hydrogen bonding. So this information actually we can use in this way. If we put such functional group or moiety which can form hydrogen bond with these two amino acids, because we have the knowledge of active site, structure of the active site, so we can use this knowledge now to develop one new molecule. Now if we look at the H41, which is very important molecule, which is very important amino acid in the active site, we can see only one phase of the histidine is utilized, another is blocked. Therefore, we can say the different part of the amino acids interact with the small molecule differently, and cysteine 145 and glycine 143 actually involve this sort of stereochemistry, and obviously it can indicating that hydrogen bonding is very important with this ketone group for the molecular recognition or for the complex formation with the protein. For this reason, we analyze all the amino acids part by part. If we consider all the parts of this amino acid, we can find only this aromatic ring is involved for the pi stacking interactions, pi interactions, or CH pi interactions. And we can see only pi stacking interactions very, very low. It is like 5% of the total interactions. Hydrogen bonding like 5%, and other polar interactions it is like more than 10%. Therefore, we can say this molecule and histidine, one side of the histidine is very important or very interested to interact with aromatic rings. Here, active site contain another histidine ring, histidine moiety. Okay, so this histidine is not at all interested to interact with pi stacking, but this histidine interested with pi stacking, interact with the small molecule with pi stacking. So mapping of the interaction of the atomic stick level is very important to develop a molecule. So if we see this molecule form hydrogen bonding, and this cysteine can form hydrogen bonding, and the C part is involved in hydrogen bonding. In case of glycine, this C part is involved in hydrogen bonding. So this information give intuition to choose functional group for the choose a functional group in a small molecule. So if we consider this active site, then we have to place our functional group in such a way it can cover all these important amino acids through these favorable interactions. And if we see this combination where it is a glycine and this cysteine, then we can find, if we optimize the structure and draw the molecular electrostatic potential map, then we can find here is a blue region which is obviously very eager to form hydrogen bonding with any group through hydrogen bond donation. This H and this H can be donated to a group for hydrogen bonding. So like this. And this is the molecular recognition process. And that's why any alpha haloketone group can recognize this center, and this SH can attack here to form this covalent bond. So these covalent interactions, as we see very first slides, this covalent interaction can possible when it forms this sort of non-covalent interactions with these two centers, and this covalent binding is driven by this hydrogen bond. Then we design this molecule which contain one alpha haloketone group and one benzene ring very near to this, because it can interact with this histidine, and then we dock this molecule inside the protein active site. Then we find if we increase the chain length, it is fine for n is equal to 1. So 1 carbon is fine here. Now, if we change the bond angle here, then the value can changes. Okay, so the bond angle change is not favorable for the favorable interactions. So we can introduce hydrophobicity, we can introduce more electrophilicity to this ring, we can introduce such group which can decrease the electron density and more decrease electron density from this center, this benzene ring, and in this way we optimize it. This methyl group is metamethyl group is sufficient and it can bind very strongly with this protein. But if we consider all other molecules which already bound, which we found in the crystal structure, and if we take those molecules and perform docking, then these values are very close to them. So it is obviously this modeling is not so efficient. So then we modify with the help of these interactions. If we see this incorporation of this amide group, one hydrogen bond can possible here, and then introduction of this amide group in between these two rings can bind very strongly with the protein. And after that, we perform the molecular dynamics to find this structure, whether it is strongly bound or not. And in this way, we can say this may be one new path for the design of new molecule which can bind with the protein very efficiently. So this study can give us these four important informations. One, we can find the actual active site amino acids. We can identify the functional group required for more efficient small molecule or drug candidate, and we can find the reaction mechanism, how this recognition process can going on inside the protein in this study, and we can find the non-covalent interaction network present in the protein active site with small molecule and protein interactions. And finally, I want to thank my friends Pranab Chandra Saha, Zareen, Sajadi, Aratika, Monami, and Rajibul Islam for contributing this work. And finally, I would like to thank my college, Lady Bhavan College, and my department. Thank you very much for your patience.
Thank you, Dr. Naeem, for your delivering an exciting and illuminating lecture. Now we are running behind the schedule, so I request the audience to ask one or two questions to Nancy Pai. There is no question, so now we can conclude here. Hello.
Yes.
Myself Rajibul Islam. So I have one question to Dr. Naeem Sipai.
Yes.
First of all, I would like to convey my gratitude to you that you have delivered a very good lecture regarding this non-covalent interaction. So my question is that is there any drug carrier needed to carry that kind of drug you have designed or you mentioned for the particular effectiveness?
No. Actually, this study is confined to find the molecule which can interact with other molecules. So here we try to find which molecule is suitable or which molecule is more efficient for this protein binding. We do not interested here to find any carrier molecules or other which can carry this molecule.
Okay, thank you.
Okay, once again, thank you, Dr. Sipai. Now we are going to our next session.
Thank you very much
for next session.
No.
Okay.
No, only the madam. No. Yes.
Thanks, Anupam. It gives me immense pleasure to introduce our next speaker, Dr. Nimai Chand Pramanik. Dr. Pramanik is a senior principal scientist of CSIR, Central Glass and Ceramic Research Institute, Kolkata. He did his master's in chemistry with inorganic chemistry specialization from Vidyasagar University and PhD from Jadavpur University. He was selected as CSIR Research Associate from Council of Scientific and Industrial Research, New Delhi in 2001. He got Venture Business Fellowship from Venture Business Laboratory, Japan in 2002 and Brain Pool Scholarship from Korea Foundation of Science and Technology, South Korea in 2004. He was the recipient of Flame of Science Award for Excellence Contribution in Nobel Cause of Science from World Science Congress in 2014 and Innovation Pavilion Award for Development of Indigenous Aerogel Supercapacitor conferred by Advanced Materials and Processes for Defense Applications in 2019. Dr. N.C. Pramanik served as a visiting lecturer at Department of Applied Chemistry, Okayama University, Okayama, Japan, and as visiting scientist at Korea Research Institute of Chemical Technology, South Korea. He was associated with the Center for Materials for Electronics Technology, Thrissur, as a scientist from the year of 2006 to 2020. He joined at Central Glass and Ceramic Research Institute, Kolkata as Senior Principal Scientist in 2020 and working till date. He has an excellent research career. His area of interest of research work is energy materials and devices and nanomaterials. Dr. Pramanik has completed 11 projects. Another 4 projects have been submitted and 4 projects are ongoing. He has more than 41 publications in various international journals and has been granted 8 patents for his outstanding research work. Dr. Pramanik is a reviewer and also member of editorial board of various renowned journals. He serves as technical expert in various national level committees also. He is a life member of Society for Advancement of Electrochemical Sciences and Technology India and Indian Association for the Cultivation of Science, Kolkata. He is also an affiliate member of International Union of Pure and Applied Chemistry, USA. Today, Dr. N.C. Pramanik will enlighten us on an important topic, translation of laboratory chemistry to development efficient energy storage devices and its applications in high power electronics. Now over to Dr. Pramanik with a request to deliver his illuminating talk. Sir, please.
So am I audible, madam?
Yes, sir. Yes, sir.
Okay, so good afternoon to all, and my sincere thanks to Anindita madam for introducing me here in this conference of recent advances in chemistry and chemical biology. I would like to express my sincere thanks to Dr. Mal and Dr. Sinha, the convener of this organizing committees, for inviting me, and also Principal Madam to give the opportunity to share my works in this forum. So I'm also happy to see one of my contemporary seniors, Dr. Shankar Prasad, they are present in this meeting, and also my teacher, of course, indirect teachers, Dr. Nitin Chakraborty from Jadavpur University, as I was doing my PhD during that time. So before going to the topics, just I recollect that Professor Chakraborty has rightly pointed that attitude of the learning of subject is most important for doing any research, leading the life, anything. So here the topic I have selected, basically it is a development of efficient energy storage devices. So to do it, how the laboratory-based chemistry helped me to translate the simple chemical reaction into a advanced material and then use the material to convert into the device and to go for a high power electronic application as a part of demonstrations. I will be briefing this. So as you know, we are doing lot of experiments, especially the chemical experiments in day-to-day in our laboratories. But sometimes we may ignore some of the changes, or sometimes we notice but not follow up. But at the same time, we should know when a chemical reaction is taking place, what way it goes, what kind of sort of control we can have on the particular chemical reaction to get a desired materials. Desired in the sense, like, first of all, we have to set a goal where I am doing, what for I am making the material, whether the material can serve the purposes. So if once we set all these points at the beginning and think on the subject while doing any experiments, it can be day-to-day laboratory experiments like simple organic synthesis, or in advanced materials like making nanoparticles and nanomaterials, especially like silver nanoparticle, gold nanoparticle, copper nanoparticle, which are now has a most attractive component for these COVID situations, because silver particles has shown very promising effect on the antimicrobial properties. So that way, so I maybe distributed the talk in different way to know what is the energy storage system. I will just briefly explain, and then come to what is supercapacitors, how the material systems affect the supercapacitor performance, and then some of the results and demonstrations. So as you know, energy is one of the top 10 priority in our society, in our life, everywhere, because without energy we cannot move. So there is energy systems are various kind of, like, there are two ways. One is the storage, another is the harvesting. So since my talk I have chosen for the selection of the energy storage, I will just mostly concentrate on the storage sector. In the storage sector, if you look into the storage, in the storage sector, there are chemical storage and field storage. Generally, the ceramic capacitor or small discrete capacitors are considered as the field-based, electric field-based capacitor storage systems, whereas batteries, fuel cells, and capacitor or supercapacitors are known as the promising storage component. Of course, battery is a well-known, because from the day one, the latent dry cell, when it started with the zinc sulfuric acid mixtures, that day onwards, it is known. Now a lot of advancement has come, which now we are looking on lithium-ion batteries, sodium-air batteries, sodium-ion batteries. Many components are coming. Of course, batteries are very good for energy storage component, but when it goes to real application, there are some part also we need to consider. One, where we are going to use the stored energy, like in a portable device or in stationary device. If it is a portable device, then size make a big sense and matters. Because once you portability, I have to fit the device within my system what I am carrying. And what are the requirement of energy rating or power rating of the device, that also need to be considered. In that way, battery is very good, as I say, is a very good storage, it is a good portability is there. But once it comes for a power-based systems, where the power is most important, critical to perform the device performance, like a mobile. When you switch your mobile running, it takes a very few amps of current while running, like maybe a few milliamps or microamps currents ratings. Whereas when you switch on the immediately silent mode to the display mode, it takes a current of several milliamps. Even sometimes it is a amps. So that means my battery has to provide the current of 1 ampere or 200 milliamperes within the fraction of seconds, whether my battery is capable of doing so. So that way, if I have to look, capacitors are mostly made for such, targeted for such applications, and so they are very good in delivering the energy in a very short time. That means it has a very high power capabilities. So coming to the storage process, there are, as I mentioned, the capacitors are basically physical or electrical field-based storage systems, whereas there are several chemical storage systems where battery plays, because battery basically electrochemical reactions. But while in the going for electrochemical reaction, we know there are two types of electrochemical reaction takes place. One is called the Faraday reaction where there will be a neat electron transfer and process changes, and another will be non-Faraday reaction. This is kind of semi field-based system or electrostatic systems where the electrochemical process induced by the electron transfer electrons but not by the complete transfer. Second point we have to keep in mind that since we are looking on these storage systems and there is a charge discharge is one of the critical. So how many numbers of charge discharge cycles it can withstand, that govern the life of the systems. So keeping all these things, I just quickly brief that in the storage system, or as I say, is a conventional capacitor. All electronic system has these capacitors that is normally called conventional capacitor or ceramic capacitor, which is nothing but a parallel plate system in where let's say dielectric components are there within the two electrodes, and the capacitance or energy storage depends on the dielectric constant of permittivity of the materials, its area and its thickness. So if you have to have a you need bigger energy, means either you have to increase the area or the dimensions or reduce the thickness. Of course, all processable devices, thickness has certain limitations, we have to see. But some application needs some more energy. So see, this conventional capacitor may not fit into the desired energy or power ratings. So to change it, there are another type of capacitor has come, which is called electrolytic capacitor, which is nothing but a similar systems, but an electrolyte is introduced in between the two electrodes where dielectrics is remain like aluminum oxide or some similar type of systems. Electrolytes are introduced to increase the charge storage capacities, but still this limits, because we know all electrolytic capacitors, if you remember, it's in the microfarad ranges, whereas some certain application requires a farad rating of energies. So that is not possible with this. So how can we make it? So with this aspect, there is a new type of technology or new type of terminology has come, which is called super capacitor. Sometimes they are known as also ultra capacitor or electrochemical capacitor, like this. So you look into the electric super capacitor or like double layer capacitor. The basic working is that there is a two electrodes. In between there is an active materials which placed in between the two electrodes, and electrolytes are involved. When we are applying the electrical field, what happens? The electrolyte dissociates and make an electrical layer at the interface of these electrode and electrolytes. And because the electrolytes are stacked on the interfaces, it carry the charges, that is the equivalent of energies. And moment you are sorting or discharging it, the charge go away and current flow through the external circuits. So now the storage depends on that how many numbers of ions we can keep on the surfaces. That will decide the amount of charge storage. So essentially, to have a high charge storage, we have to have a more surface available to form the electrical layers or electrical double layers at the interface. This is one of the important criteria for the material to select to perform the supercapacitors. So essentially, as I said, it should have a high interfacial surfaces to maximize the charge densities, and also should have a conductive nanostructures for the fast charge transfer. Because as I say, the fast charge transfer is also an important phenomena where the charge has to be delivered to the load or external circuit very fast, then only it will meet the power requirements of the particular applications. As again I have mentioned that there are several kind of systems are known, out of which if we plot it like energy versus power things, you see the fuel cells, it is a system which is having a very high energies, but its power is, we can see its power is very, very low. Whereas the conventional capacitor or even electrolytic capacitors, powers are very high, but the amount of energy that delivered from the systems are very poor. So there are intermediate, so many systems has been where we see that supercapacitor is the system which will have a very good power as well as very high energy. That means it's a bridging between the two systems with a similar kind of, with a like synchronized energy power relationships. So this has come for a lot of applications in terms of technologies and as well as the processes for storage systems. So as I said, that there are different type of storage systems, kind of capacity, normal conventional electrolytic capacitor, a double layer capacitor, or all these are considered as supercapacitors, out of which the double layer capacitors are considered to be much better because it has the number of cycle lives are much high. Charging discharging time is very low, as well as it can gives a better energies. With this, based on that, there are a lot of applications are coming for supercapacitor. Already some are already established, some are yet to be. So we can see these capacitors can be used in the consumer electronics, all power electronics, hybrid battery systems, even the smart grid system for load levelings, railway tractions. Wherever the high power related applications are there, it can be utilized, and some has already established. One of the example is that we are looking for the electric vehicle, for the electric mobility systems, where the battery is the one of the component give the provide the energy to the system for running and as well as the accelerating, braking, all these purposes. But if you look into this batteries, as I say, batteries are very good for giving a constant energy because it voltage profile, charge discharge profile is with respect to time is unique. But when it goes for the accelerating, you need high power to give to the motor or high current to give to the motor, which when connect with the systems, the battery sometimes fails and it cannot deliver. And second is the storage of the charging of the batteries. So in order to incorporate those things, now all the electric vehicles has added a component called regenerative storage. Means while car is moving, it is utilizing the energy from the battery systems. Whenever we are making the braking, so if we, with the braking, the kinetic energy is converted into the electrical energy by a double bidirectional converter, and then energy to be stored into the battery. But the problem in the battery is that generally batteries charge takes place at very low current. So whereas the bidirectional current, since it is a momentarily generated through a braking process, so the total amount of current cannot be stored or charge cannot be stored within the battery. So it gives that most of the energies get lost. Even we introduced a new electronics, new system to store the energies. So this is basically the limitations of the batteries on them. Their ultra capacitor is the component, or supercapacitor is the component which can take any current, because supercapacitor the charging and discharging profile depends on C into V by T, where C equal to I into T by V. That means that any current, it can take if there is no other interfering components are available. Similarly, like we know that internal engines, most of the car engines are starting with a self-start component where a battery is there. But on the battery, we know in the cold time or especially low temperature zones, battery cars are not getting started. There are mostly two reasons are there. One, it may be the faulty of the battery, or most of the cases it is non-performing of the battery properly. Because to understand that how the internal IC engine starts, when it put the cranking key, it generally requires around 92 kilojoule of energy to start a car engine. But out of that 90 joule, it has two components. First component, basically it's around 50 joules, which essentially to overcome the torque part, and second part around 40 joule is essentially gives the ignition to the fuel. So when we on the switch or crank it, try to crank it, what happens that first is battery gives the energy, it gives the slight motion to the or overcome the torques, but by that time battery voltage drop because of high current drawn for short durations, and engine cannot ignite. what happens? Sometimes we heard that the crack sound, some sound is coming, and the car is not starting. We wait for some time, and again it starts. So to avoid those things, if we use a supercapacitor, then it can be smooth charging. And nowadays, many of the advanced cars has the supercapacitor parallel connected to get a faster charges, so that even in cold country, cold area where the minus temperature is more prominent, like Ladakh and other areas, it will be useful. Similarly, for the storage systems, like nowadays we are talking on harvesting of the solar energy, solar panel, even that in our house also we have put the panels to store it. But if you see that most of the cases happen, what the efficiency of the panel around 60 to 70% are being utilized, because whatever the energy produced from the panels to be stored in the battery, whereas the battery is incompatible for that. Because the batteries, as I say, charging procedure, most of the house batteries are with the lead acid batteries, and its charging is very, very slow. So energy produced, but it cannot take. That's why it is like a 60 to 70% of the panel efficiency is converted to the battery, so that 100% battery gets stored. So it means even after harvesting, designing the panel, everything, we are wasting the energy. After harvested energy, we are wasting. So to improve the efficiency of our storage of the harvested energies, whereas supercapacitor based systems can improve, we have established in our lab at CIMET. Okay, I forgot one point to mention here, that whatever I am explaining, this is my past work, what I have done at this CIMET Thrissur during my period. So, so we have established a plot system where 100% efficiently it can store the energy, and after the storage it is a parallel connected, and after that it can go to the battery also. So it means even up and downs of the sun can be accommodated by the supercapacitor based systems into the storage media. So what we say is that now we are talking the battery capacitors all are there, but where we are going to use this and how we are going to design the system, because all the cases we are talking on devices. So once we talk a device, means where I am to use the device, what for we have to use that we should understand. So like if you want to use the specifically for energy applications where the energy is most critical, like I have to use a storage system in my clock or wristwatch. That means where constant rated energy is required, which is very, very slow discharge rates, there only storage is considered. Whereas if I want to use this electric vehicle, where is that power is basically instant, there will be a lot of up and down accelerations. So power delivery is most important. There are some application point we have to consider. And whether I am to get a fast charging or fast discharging. Fast discharging is generally desired for the power application, but whether I am to get a very fast charging, that is also to be considered. For that, because all the cases design aspect of the capacitor accordingly one material system will change, it has to consider things. So again, another point I would like to highlight here. Once we are going for a device is a complete system which is a assembling of lot of small components, small or minor components also. But maybe one major component is there which governs the property, but at the same time there are like. So in the capacitor, if one say, if you look into this, there are so many components in a single cell involved. Even there are some more, but like on the active material, which basically govern the properties of the device and performance. In addition to that, current collector means the material has to be placed on the current cutoff from which the outside circuit current is passing through the outside circuit. Then the separator means that both the electrode has to be separated properly, and then it comes to the electrolyte. What kind of electrolytes are going to use, what voltage, because electrolyte determines the operating voltage of the cells, and the terminal leads. Obviously this leads should be low resistive metallic components, and sealing also, because it should be hermetically sealed, otherwise it may leak the electrolyte. It may damage the systems, contaminate the electrolyte over a time, that's all. So, as I mentioned, the major important part of that all the devices, or especially the capacitor device, is the material, which governs the many properties like its energy content, its power delivery capabilities, its energy densities, and also processabilities. There are several material has been already established and people are working on. One is the activated carbon, which is basically derived from coconut based bio waste or coconut based material, because it has a very high we can produce very high large surface area of the materials. It is relatively cost, and most commercial components are use this. But it has certain limitation also, because it cannot give a high energy density. Means although materials are very good, or from commercial exploitation, costs are relatively low, but the charge density point of view is very less. Its energy density is hardly 2 to 3 kilojoules watt hour per kg. For the next material comes as the aerogel materials. I will describe details on the aerogels, because it's my area of work where we have established the thing. It is a three-dimensional network materials or network structured materials made of the carbons. It exhibits very high specific surface, which is one of the primary requirement for making a capacitor electrode materials. It has a lot of open pores that enables us to move the electrode within the electrolyte within the structures, and also being the network connected structure give good electrical conductivities that enables transfer of electron from the electrolyte interface to the external circuits and through current collector modes. It has low material densities, so means my overall density is so weight of the system will be low, and also of course the relatively low cost, and it can be produced in bulk. There are many materials are known like carbon nanotube. Bulk production is difficult, so once we go for a device for commercializations, it may not be useful, may not be possible to upscale it for as per requirements. So there are several other materials are also known. Because of I think we are a little bit late also, so I will just keep some of these. So our primary focus is to develop the aerogels. Before going to that, we should know few of the terminology. This may be essentially for the students who are there. Say we know as a solution means is homogeneous mixture of two or more components, where means the solute molecules are uniformly or homogeneously distributed within the dispersed phase or medium, like in water or other solvents. But when it forms a gel, it becomes a reverse systems. Reverse in the sense where the liquid get dispersed within the three-dimensional network of the nanoparticles. So, an aerogel is the replacement of the liquid phase into the air. Basically, aerogel is called a air-filled gel, where all the nanoparticles are interlinked in three-dimensional networks and the pores are filled with the airs. So making an aerogel, that means interacting the structure is very, very important, and we need to look into this particular methodology, how to get a three-dimensional network remain intact, what remain in the gel type. So, like a common convention like reactions, if you generally the alkoxide based system, silicon alkoxide or others, when it gets hydrolyzed, it forms a basically alkoxide hydrolyzed, it forms the silicon O or similar type of metal oxide bondings, and then these bondings are again joined through condensation reactions to form the metal O metal type of structures, or it can be through alcoholic condensation process also. So at the end we are getting a MOM or element to oxygen linkage. But the linkage is again depends on so many process like various conditions. Like if you go for an acid catalysis reaction, the linkages are going to be a polymeric type of structure formations, where we can go network structures. Whereas if you go for a base catalysis process, but catalyst hydrolysis takes place with a base catalyst, then it go for a colloidal transformations. That means it will form initially a discrete smaller particles, and then these smaller particles will join together to form a network. But still at the same time, so when we go for a, because gel, essentially we need to have a gel network formation. Network is formed, but once the network is formed, then how can we take out into the liquid which is present within the network? Generally that is done through a special drying technique we call the either freeze drying or we call supercritical drying. So as you know, generally all the cases we dry the liquid or dry the system by conventional drying process, where basically solvents are evaporated. When the solvent goes into this boil above the boiling point and get evaporated from the systems, but during the evaporation process, it ruptured the network present within the gel or system present. So we have to have the several special critical drying process, where it will not affect the pore shrinkage or rupturing of the networks. So that is called a supercritical drying, because if you look into the pressure temperature profile of any solid materials, there in all the cases it has three phases. One is called triple point, another is called critical point. That means at the critical point, there will be no phase boundary exist between the liquid and the vapor phases. So in the particular that point, the liquid will be coming out or diffused within the system by diffusion process without hampering the what's called the phase differences. And once it reaches to the particular point, material will have several property, advantageous properties, like all inter-component will form like a single component since there is no phase boundary. And by the way, there will be no surface tension. Mostly the surface tension will be very zero, so there will be no shrinkage during the drying process takes place. So network will remain intact, whereas the inside component will come out by the systems. So every material has its own critical points. Like water, it has a critical point around 374.5 degrees centigrade with a pressure of 22 megapascals. Whereas the carbon dioxide temperature is low, around 31 degree, and its critical pressure is around 7.3 megapascals. Whereas the acetone, it has a 235 degree and 47 megapascals. So we generally do for that go for a supercritical drying. It has certain advantages, and implementable process also. It can be implemented in a bit higher scale also. That's why whatever experiments we have done, we made it with through supercritical processes. As I say, the simple chemistry, like if you look into this top part, it is basically nothing but a phenol formaldehyde reactions, where we have used dihydroxy enzymes called resorcinol in presence of a catalyst called simple sodium carbonate. When the sodium carbonate and phenols aldehydes are reacted, they form a dihydroxy such type of bondings, and then at the end it forms a network having a wide range carbon networks of polymeric gels comprising the resorcinol formaldehyde, which forms all the inter-resorcinol rings are interlinked with the either CH2OCH2 rings or CH2OCH or sometimes directly CH rings or CH2 rings also. So now this is generally laboratory happen. We do it also. But after doing this, the network formations, what we need to tune the properties of the pores. So now the gel formation, if we control the process, we can get a proper tuning of the gel networks of the organic gels, which later on will convert into the carbon process. So what says that once the polymer is formed, these polymers looks like a interconnected structures. Basically, although apparently looks like a blocks, but it has its own interconnectivities, and then go through supercritical drying, will get a only network structure where pores are filled with the air. So this way we started with take this particular chemical reactions and process it and form a material like a carbo-organic based aerogel, which we control under control atmosphere to get a graphitic carbons. That we named as the carbon aerogels, and process into the active material for the supercapacitor and fabricated the cell out of it. If you look into this is some of the pictures. We see the structures, microstructures, where the very neat tiny carbon atoms are interlinked with having the pores properly. Surfaces are there interconnected. This is fine out. And as per the properties also investigated, like XRD, it shows that graphitic carbon means like have a layer like lattice structures. It will gives a better good electrical conductivities. Porosities are around 70 to 80%. That means that is it all not like a pure graphites. Density is also coming to the around less than 1 gram per cc, which is much lower than the theoretical density of the graphite. And its electrical conductivity and surface areas are quite reasonable. Good. So these materials are tested for various of these particular applications, and it is compared that this our material what we have developed indigenously is much better than the imported materials. So on all respects, if you look into the last line, this is from the specific capacitance, surface area, because the surface area again it is tuned with respect to the conductivity, because which is one of the part requirement of the to use this material as the electrode. And then these are the indigenously we have designed a lot of machineries to establish the process, because these type of things are not available in India, so we have designed locally with the machines, and they finally make the cells. After doing these things, these are the performance of the charge discharge properties of this, make the cell prototype smaller cells, and then see the how the charge discharge is behaving, how are the cycle, what is the temperature profile, how material properties interlinked with this final device performance we have done. And after this we have gotten several patents, because process is not the composition maintenance has a commercial importance, so we have gone for several patents for them, filed the patents. After doing it, there is a huge, the electrical mobility component has come, and there is a huge requirement also has started. Government has given a lot of initiative and encouragement. With that, we started and established the process into a pilot level. As you know, generally we laboratory do few gram basis, but this material requirement is very high. So we establish a plant in a where we can produce a material all 5 kg per day in a single batch. So 5 kg means it can give around 25,000 piece of capacitors if we say as 1 farad capacitor per day batches. Not only the 5, this is the entire process has been made, like we make a reactor. Out of the reactor, once we get a gel is being converted into the aerosols. This is the plant for making aerosols, and then established into the furnace. This furnace chamber is around 1 meter by 1 meter by 1 meter, where we can carbonize 100 the material in all 5 kg material put inside and get it. Once the material is being processed, then there are the machinery is also designed and fabricated to get a electrode for processability, like machine processing, and from there you convert the cells. So this is like the material tested performance. Also, this gives a good XRD patterns, which is very much close to the graphitic structures and desirable also. The pores are also, you can see the fine nanoparticles are interconnected. That means what we had envisaged is that it should have a network structure. It is already there and has given a good surface area also. So the basic, intention is that to develop this process, but indigenizing the process in the laboratory like an institute like a CIMET. So there are a lot of problems are there, a lot of hurdles we have to overcome. But the main silent feature or beauty of this particular process we have established here, this is a recyclable systems. That means the supercritical fluid, here we use basically the liquid carbon dioxide, is charged only once, and then it is going recycling, and automatically entire process is SCADA based on electronic based systems and recycle 100%. So there is no carbon dioxide or nothing is coming out to the atmosphere to cause the pollution problems. Because these are the, once we go for establish a plan, like environmental issue will be one of the points. So we establish it, and we have tested all the materials again from the laboratory scale material, and once you upscale it bigger batch, whether the batch are matching and giving the desired performance, that also been tested. And not only that, all material we have sent to the ISRO, because ISRO has it on their test facilities, So they have tested it and materials are found good. So once the batch material are good, then we try to establish our own methodology or own machineries to productionize it in a semi-levels. So we have designed all the machineries. Again, we have and fabricated the cells. We can see here we can make electrodes of around 1,000 meter per month, or like in a spool form with having 50 meter per spool. And most important part and duty is that generally when we make a material convert into the electrode of like flexible natures, it lost its surface characteristics to some extent. But here we establish a methodology for making or converting the material into the flexible electrodes, where there is almost negligible loss of the surface characteristics. We can see here the basic material is having around 1400 meter square per gram as surface area. After converting into the electrode direct surface area is giving around 1375. And with the pore structure, pore volume, almost all are remain similar. So that gives the converting the process of the material, converting the material into its usable form, while electrode forms is unique, and we have got a patent out of it. And then we again, because once you get the material, now device comes cells. So there you have to have it appropriately, because cell means you have to give a proper ratings, like what Farad is required, how many values cell is required, what will be its cell parameters like ASR and other things. All has to be defined before fabricating the cell. So machine has to be tuned accordingly. We have done, and we made a cell, wide range of cell starting from 0.47 to 50 farad. We have designed, and most of the cases you can see the charge discharge profiles are unique from all the cases. And cyclic voltammogram profile, if you see, it can go around 700 farad millivolt per second, means almost 1 volt per second. That much fast charging is possible with these type of systems. It gives very low electrical impedances. So with this, and materials are, all the cells are also tested. Even we have tested the life cycles, number of life cycles with respect to temperature, how the capacitance and ESR, because ESR is one of the component for a device which should be as low as possible. Otherwise, there will be large leakage will come from the systems. So that has been tested, which gives very promising and usability to show for the real application devices. Even the batch to batch performance, like when you are doing a batch selling, like one batch on every batches, that should not be too much of tolerance, or differences should not come. So that has been also tested, and it gives a good result. After doing this, we have made some proto laboratory demonstrations, like funny things like running a fan, doing a toy car, lighting a light, like this. But these are all silly, smaller applications. But to real application to go, in 2017, 2018, the Election Commission has called for a brainstorming session and asked that whether it can be utilized for the electronic voting systems. In the voting systems, if you look into this, nowadays in the voting system there are two components. One is the voting machine, and another VVPAT, which is basically voter verifiable audit trail, which is nothing but a printed slip of the vote casted. So that VVPAT machine basically uses 30 batteries. If you see inside the VVPAT system, there is a 30 pencil type of batteries, and these pencil batteries are highly manganese dioxide based alkaline battery, high power alkaline battery. Even these batteries are not produced in India. We have to import all these batteries for every machines. You can imagine that how many voting booths are there, how many VVPATs are running in particular elections. So, but the problem in this, even giving the 30 battery cells, if you look in the current charge discharge profiles, the average discharge profile of the current requirement for a VVPAT is around 0.5 amps for voting during the voting cycle. Whereas whenever switching on putting your voting roll your vote or cast your vote, the surge current requirement comes around 3.5 to 4 amps, which difficult to get even from the 30 cells out the battery at a stage for a momentary second or few seconds. So the Election Commission asked us that whether we can do something on this. Then we have taken the project. We established these are the difficulties what I have shown. we established, I will just keep these things. We have established systems, like you can see the cells are stacked into the systems and tested in the real VPAT. This is done at the ECIL. They have done and tested, it gives around 2,500 votes along with a 15 battery cell, because battery anyway it has to be there. Out of the 30, if you see here, out of the 30 battery cells, 15 is for balancing the voltage. Other 15 cells are kept in parallel to match avoid any failure in the surge voltage, surge current. So now we are replacing the 15 battery with another our indigenous supercapacitor cells, which shows a very good promising results. Like it has now come around 3,000 volt also. Almost project is over. I think this September will be the closing of the project from the laboratory end. Then it will go for this project is done by the ECIL, because voting machine, these things only election commission, Electronic Corporation of India Limited, that ECIL at Hyderabad, they are only authorized to do all the VVPAT machines related awards. So they have done it. Like now this has, you see the 15 out of 15 battery, one portion has been replaced with these our capacitor cells, this portion, and the other portion remain the battery, because size also has to design accordingly that it should fit with the existing battery VPAT systems. This is tested. And apart from that, another properties comes like a leakage current. Generally, leakage, once VPAT comes into the system operations, is it charged battery, how fast it should not discharge also. So we have tested the leakage. It comes around few 100 to 200 microamps is self discharge. This is quite reasonably good, and it passed the test. So overall, we say this whatever the mesh system we have developed is indigenously is good to go for a indigenous application from high power electronic applications. There are some more applications are there. So in addition to that, we are also doing some hybrid systems like to go for much higher energy, but system is yet to be established, because hybrid system basically called the hybrid supercapacitors. The phenomena is entirely different, where it goes for a metal redox systems, and the metal redox system generally works in the aqueous mediums because its protons are involved in the system. So proton-based system, it goes only the low operating cell voltage. To see, you have to maybe we need some much more watts. That's all. So performance apparently it's good, but the ESR point of view, they are still the much higher side. So it is need to be reduced further. So in conclusion, we said that we have established and chosen a indigenous, simple laboratory chemistry, converted into the materials, and then make a laboratory grade process. Then establish the pilot level process, not only the material device fabrication. Now we are going ahead for a application of the indigenous component to a critical indigenous applications like VPAT. So with this, because all these works essentially require the fundings from various sources like Ministry of Electronics and Information Technology, Ministry of Science and Technology. BRNS also has given a good amount of fundings. And these are the last batch of my students when I left CMET in 2020, students and faculty, although of course. So thank you so much. I think I have crossed my time. So any questions or queries, I'll be happy to answer.
Thank you, sir. Thank you so much for your wonderful and informative talk. As we are already going behind the scheduled time, so I am requesting the participants to please put forward one or two questions to Dr. Pramanik.
Hello.
Hello.
Yes,
Hello, Dr. Dev.
Hello.
Can I call you Sampaddar?
Have you used any supercritical fluid in your work?
Yeah. This is here supercritical fluid is the carbon dioxide. Supercritical carbon dioxide.
You have used it?
Yeah.
Is there, where are production plan in India?
System is there for supercritical. Say, basically, liquid carbon dioxide is converted into supercritical within the systems.
But it needs a temperature zone that to convert it to supercritical.
You have to very critically and precisely control the temperature and pressure. Because supercritical carbon dioxide critical temperature is 31 degrees centigrade and pressure is around 72 around 75 bar pressure.
71 or 22 like that. Okay.
Yes.
Thanks. You are fantastic. Is that there is no time to discuss or interact. If we get time, I think that we can interact more and more. Okay. Thank you very much.
Sure. Anytime.
Any more questions? So now let us move to the next session. We have come to the fourth phase of technical session. Our next speaker is Dr. Nirnay Samanto from Germany. I would like to invite Mr. Prithviraj Shashmal to chair the next session and to introduce our next speaker. Over to Prithviraj.
Thank you, Arundhati. Am I audible?
Yes.
So good afternoon to all of you. It's my great pleasure to introduce and welcome today's next resource person, Dr. Nirnay Samanto. He was former research assistant of Professor Dr. Ebbinghaus Lab, Institute for Physical and Theoretical Chemistry, Germany. Regarding his academic career, he has got a very promising academic career. He has got his BSc degree in chemistry from Ashutosh College. He has completed his MSc from Ramakrishna Mission Vivekananda Centenary College. He obtained his PhD degree from Department of Chemical, Biological and Macromolecular Sciences, SN Bose National Center for Basic Sciences, Kolkata, under the University of Calcutta. His thesis was entitled Studying the Effect of Different Consolutes on Protein Conformational Stability, Hydration Dynamics and Activity. From the year of 2017 to 18, he was Extended Senior Research Fellow at SN Bose National Center for Basic Sciences under the guidance of Professor Rajiv Kumar Mitra. From the year of 2018 to 2022, he was postdoctorate research assistant in Professor Dr. Ebbinghaus Lab, Germany. Dr. Samanto, along with his research group, has authored and published many papers in national and international reputed journals. Now I am requesting our next honorable speaker, Dr. Samanto, to deliver his valuable speech. Over to Dr. Samanto, please.
So am I audible?
Yes.
Yeah, and you can see my presentation, right?
Yes.
Yeah, okay, thanks for this nice introduction. And so first of all, I would like to thank the organizers for such a nice webinar, mainly for this great topic that recent advances in chemistry and chemical biology. So yeah, this is really very relevant nowadays, because to understand all the biological process, definitely need chemistry to explain everything. And yeah, I would like to also thank all the previous speakers for such a great talk. And also some innovative ideas, and also about the education of science. So it is really great for me to take part in this seminar. So yeah, without further delay, let's get started to share my work. And yeah, I'm also excited to share my work in front of the college students, and I'll be very happy if you interact. And yeah, please feel free to come to ask any questions if you don't understand or if something is not clear. Okay, so yeah, so first you can see here one picture. So first let's visualize this process. So first I would like to show you one thing. Like, I think you definitely know, or maybe some of you, maybe students, don't know the details about the protein. So protein is actually one kind of like biomolecules which is made with some amino acids. And you can see that these are can you see my I think you can see. So imagine this is one protein, and yeah, like it has like different structure, like alpha helix, some beta sheet, and it has some particular form. And interestingly, protein become functional in its native or functional form, but in some condition it became unfolded like this, and then it loses its activity or functionality. And always this protein, like initially in the cell, protein are like unfolded state, and then they right away after synthesis became folded, or they get a particular shape to do the particular work. And here I am trying to visualize this thing that, okay, there is one equilibrium between folding to unfolding, and you can see like some proteins are here like a compact structure, but some are like unfolded. And you can see this is so far just imagine that this is one sphere, like some liquid, like I will tell what is this later. And here you see that there is some heat sign, so that means, okay, so for this we need some heat stress. So yeah, with this I would like to show my topic today, that so I will discuss about crosstalk between protein folding, unfolding equilibrium, and liquid-liquid phase separation in stress granules from test tube to in cell. And yeah, what is, I think you definitely know from your chemistry class what is liquid-liquid phase separation, and yeah, what is stress granule, that I will show within a few minutes. So one question in biology, that how do the right proteins, RNAs or DNAs, organize themselves in these crowded millions or like billions of molecules? So imagine this is one model made by Good Cell. So you can see that lots of biomolecules. Is there any problem? Let me check. Is everything fine? I guess so. Okay. Yeah. Okay. So this is one model of the cell, and you can imagine that, okay, there are lots of molecules are here. So now the question is that, okay, how cell manage to organize the proteins and RNAs so that they do their job, and all the proteins or RNAs do their job in a specific way. So how it is possible in this crowded environment? Well, so you can say that, okay, so cells organize the molecules with some membrane bound conventional organelles, so that you know from the school level biology class. So for example, like mitochondria, lysosome, so all these particles, all these organelles, you can say that teeny organs of the cell. So they are membrane bound. So at least we can say, okay, these the like proteins, RNAs, or particular proteins, they are guided by some membrane, and then they can do their job very easily. But what about the proteins or some other biomolecules in the cytoplasm or inside these organelles, because they are not membrane bound? So that is one question, that how they manage. And with this question, I would like to show you one video here. Like you can see here this video, that some greenish proteins, or like protein RNAs, they are like kind of liquid-like. So they are, you see that they are dissolving, they are fusing each other, so they are really liquid-like. So and here, this is in the human cell, you can see some particles, some like condensations are growing, and then they are fusing together. So they have liquid-like property. So this is one great discovery recently, and I have to mention definitely the name of Professor Hyman from Max Planck University and Cliff Brandwin from Princeton University. They are the pioneers for this work. So they found that, okay, these particles are actually, it's called like membrane-less organelles, which has like lots of proteins, RNAs, and they bind each other by this liquid-liquid phase separation. This is really a great discovery, because I'll show you why. So they are kind of like goodie bag, and why I will tell you. But before that, let me remind you what is like liquid-liquid phase separation. So that definitely we know from our daily life that this is one mixture of oil and vinegar, or you can also imagine water in water oil mixture. So you can see that it phase separate. That means one liquid phase separate from another liquid. So that's what we call liquid-liquid phase separation. Even from your from your chemistry lab, I think definitely you already did. Some of you definitely did that. We did this phase diagram of phenol water system. Okay, so that definitely you know. So yeah, why this is so important to understand this thing, or why this topic is so so well studied nowadays. I think these membraneless organelles, they are not new. What is new that to understand their mechanism, how they form. So that was new, that it forms via the liquid-liquid phase separation, simple chemistry behind it. And why this is important? Because all these membraneless organelles are engaged in lots of cellular work, like signaling, transcription, translation, enzyme activity. Let me take the laser. Yeah. So you can see it like, yeah, the signaling and enzyme activity, some stress response. That means if a cell gets stressed somehow by heat stress or by some oxidative stress, then the process could be hampered by some protein aggregation, or it can create some neurodegenerative diseases. So all these processes are involved in this liquid-liquid phase separations. And there are lots of membraneless organelles. So here you can see that, yeah, there are lots of, and here I will only focus these stress granules, which is like one stress granule in the cytoplasm. Also some membraneless organelles are found in the nucleus. So yeah, I will not talk about all, but yeah, mainly the stress granule. So now imagine that this is one part of the cell cytoplasm where this protein folding, what I already told, the native to unfolded form, this equilibrium exists. And in certain condition, like for example some stress condition, this unfolded form could be transformed into the misfolded form. This misfolded means that it has like some partially folded state, and that misfolded form could transform irreversibly to the aggregated state. And that is dangerous, because we know this aggregation or fibrillar state of the protein is responsible for some neurodegenerative diseases like Alzheimer, Parkinson, mad cow disease, Huntington disease, amyotrophic lateral sclerosis, or ALS disease. And if the protein form in this state, so then it is not possible to come back to this functional native form. So that's why it is dangerous. But fortunately, cells have this protein quality control machinery, for example, like chaperones, which can prevent this aggregation process. How? So they can bind to this unfolded or this misfolded state so that they can come back to this native state. So that's the beauty of the cell, that it has itself some mechanism that can prevent this aggregation. But of course, it has some limitation at some point. For example, some aging condition, this process cannot take place. And after this recent discovery of this biomolecular condensates in the living organism, what we learned that inside cell, we found some liquid-like stress granule, that what we showed in the last videos. And here the stress granules means that when you give some stress condition like heat stress, for example, some fever could also generate these stress granules, which is nothing but some combination or accumulation of proteins and RNAs, and they combine each other by some non-covalent interaction. What I think Naim very clearly explained you what a different mode of non-covalent interaction. So it could be protein-protein interaction, or could be protein-RNA or protein DNA interaction, and then they form stress granules. And what we learned from the literature, that this misfolded form or the unfolded form, which is not yet very clear that which particular form, can drive into the stress granules. And if that happens, so what would be the advantage? That this aggregation process would be stopped. So we can tell that this protein, so this stress granule formation is one parallel mechanism to stop this aggregation process with this protein quality control machinery. So the problem is that So I think that this is liquid-liquid phase separation, or they form via liquid-liquid phase separation. So this is totally fine. Then they would be still in equilibrium. But the problem is that at some point, like for example, with aging, this liquid form can be transformed into the toxic solid aggregates, and that's the dangerous thing. So this mechanism, how it happens, it's not that clear so far, and that's why scientists are interested to study and to explore this field. So here I will highlight here one particular protein which involved in this amyotrophic lateral sclerosis. You can see here the symptoms, okay, and here SOD1, which is superoxide dismutase 1 enzyme, is responsible for this amyotrophic. Responsible means when it is unfolded or partially folded. When it is functional form, then it's perfect. It can it actually function to like dismutase some superoxide radical to some non-toxic hydrogen peroxide or less toxic. So that's the role of the superoxide. But when it becomes unfolded or misfolded, then it becomes toxic and it will form some aggregates, and then it causes, for example, these ALS diseases. So here one statistics, like from the ALS disease, like 10% is due to the mutation or familial ALS, and 20% of the SOD1 is particularly this SOD1 protein. 20% of this familial ALS case is due to the SOD1 mutation. That means 1 out of 5 patients is due to the SOD1 mutations. And what is mutation? That is like, okay, one protein has particular amino acid chain, and it is really very specific. But sometimes what happens, one amino acid could change, and that's called the mutation. And even by the single point mutation, the protein structure could change. Yeah, I will show you that how it changed drastically. And what we found in the recent literature that this SOD1 protein, mainly here full-length SOD1 or the functional form, can co-localize to the FAS, which is like fused in sarcoma, one protein, one RNA binding protein, and that is one stress granule marker. So what we found that this SOD1 can co-localize in this stress granule marker. So here you see one image, like super resolution image, like SOD1 A4B, this is one mutant, like and this one is the FAS protein. And when we merge together, like this green one is the the FAS, and the red one is the SOD1. You see that they are co-localizing each other. And when mainly these mutants are co-localizing more, like this is wild type or the native form, and all these others are the mutants, and you see the percentage of co-localization is higher for the mutants. And it is hypothesized that when they are mutated, they become like unfolded or misfolded, and then they co-localize with this stress granule. So now the question is that, okay, what is the energy landscape scenario? So we know that intrinsically disordered protein, for example, this FAS is one intrinsically disordered protein. So it formed like, this is like intrinsically disordered protein, and then it formed like liquid droplet, and at some point it formed the liquid to solid phase, which is like toxic. And the folded protein, it has like this unfolded structure, which is unstable form, and then this is the folded form, stable form, and then this is partially folded, and so on, like the oligomers, amorphous aggregates, amyloid fibrils. Now the question is that which folding state actually interact or with this droplet or this or how they form this liquid to solid phase transition, that is still not that well known. So with this so that's our aim, to explore this field. And what we did actually, like we take this stress granule marker FAS. So yeah, we can say that, okay, when it forms the stress granule, or like we label this FAS protein, and then we know, okay, in this place the stress granules are there in the cell, in the live human cell. And then we took this particular SOD1 protein varying different single point mutation. You can see all this colorful mutation site, and with this we can vary the stability of the protein, okay, or the structure of the protein, and then we try to understand the interaction between this FAS and SOD1. So yeah, like thanks my previous colleague, he already build such nice protein. So this SOD1 is one truncated version. So this is very good to use because so we give some freight there, like some donor fluorescent and acceptor fluorescent protein. And then if we give some like heat stress or anything, if the donor and acceptor distance go away, then the freight, I think you know maybe already the freight, like the fluorescence resonance is transferred. If the protein become unfolded, then there would be block of the freight. And by that, we can track very easily the protein structure and the protein stability. And by the single point mutation here, this is the stability like delta GH at 37 degree, because that's the cell culture temperature or our body temperature. That's why the stability delta G is calculated at 37. And you can see that these are like stable mutants. So the stability is decreasing in upwards. So here you see that these mutants are like more or less stable. And after some point, so it is going up. That means they are going destabilized. So you can see that the spectrum of stability only after the single point mutation. So in the cell, sometimes randomly it could happen that the protein become mutated and the stability is totally gone, and the protein become unfolded, and then they can form this aggregation. So with this, we took some of these proteins from here, like some intermediate stability and some destabilized one for our purpose. Now, briefly, let me introduce the strategy here. So what we did to study the protein stability of the structure, what we did, we did the wide field microscopy, and which is based on the freight imaging, okay? And then we give the temperature jump by using IR laser, and we give this temperature jump very fast so that we can track also the kinetic of the protein unfolding. Okay, so that's the beautiful technique which was discovered by Professor Ebbinghaus during his postdoc, and this is in the wide field microscope. So by this method, we can track the protein folding, unfolding, thermodynamics as well as the kinetics. And the beauty is that we can directly probe the protein unfolding phenomena in the live cell. Okay, so you can see, so this is one human cell like HeLa cell, and we can track by this method. And then what we did to understand more precisely, we did this study like more like from chemistry background in the dilute solution, and also in some cytomimetic solution that I will talk about more details later. And finally, we also checked our result, or we explain our result by the LBMT simulation, but here maybe the time would not permit to show all these things. So and then what we did after the stability measurement in the cell and also in this in vitro system, what we did some sequestration or the partition coefficient measurement by using the confocal microscope. So here you can see the green fluorescent protein in the live cell, and then you can see some blobs or some condensate in the cytoplasm. So that we calculated the partition coefficient. I think you know from the chemistry knowledge what is partition coefficient. I will also show you the formula. So let's see then what our result is. So here what we did, as I told, that first is here one stress granule marker, and we took in the HeLa cell, and then we transfected particularly this protein like SOD1 barrel with fluorescent like ACGFP here, and then here we studied like how this SOD1 barrel with the mutants what I showed you, they are accumulating in this fast droplet. So here, like some representative or some exemplary image. So this one, it has like, you see that this is like red channel by some hemisphere fluorescent, and this is like one green fluorescent. So that we can track both protein. So here, and you can see here from the merge image, like one is green and one is red, and when they merge together, they become a bit more orange-like. So we can say that okay, both are together. And here, so this is like SOD1 barrel channel. This protein, and this is the fast protein. So what we did actually, we took the cell line like human cell, HeLa cell, and then we give some heat stress, okay, at like 43 degrees Celsius. We can imagine like more or less similar to fever temperature. And then you see that the proteins, initially they are very dispersed, or this fast protein is in the nucleus, and after giving the heat stress, you see here some bright spot here. That means that they are forming this condensate, which is like more liquid-like. And here in the SOD1 Babel channel, you see here for this wild type, there is nothing here in this region. But when we see these mutants like G93V and F4V, so this is like one position, like G means some amino acid glycine at 93 position is replaced by valine. And for that, some material property or this, what Noam already introduced, this non-covalent interaction will change, and depending upon that mutation, it vary their accumulation. And exactly what we found here, for the mutants, we see that, you see here, they are colocalizing. Colocalizing means Faz is there, and also the SOD1 mutants is there. And to be more quantitative, what we did, we calculated exactly the this SOD1 protein enrichment in this particular stress granule region. So what we did here, we tracked this stress granule by the software, and then we calculated inside by outside intensity. That we can say it is proportional to the concentration of this both protein. Okay, so what we did, we calculated only in this SOD1 channel to calculate the SOD1 enrichment, and this is the formula of this we can say local apparent partition coefficient, that mean fluorescent intensity of region 1, that means the inside, divided by this surrounding. Okay, so by that we can calculate the enrichment of this SOD1 protein in this stress granule region. And what we found here for all our mutants, that here for the wild type, you see that SOD1 enrichment is 1. That means, okay, there is no biasness in this stress granule. But we see for the mutants, it is increasing. The partition coefficient or SOD1 Babel enrichment is increasing. So that very nice result that, okay, with this mutation, maybe it's like the stability is changing or the structure is changing, and that's why they are accumulating to this stress granule region. And then we ask the question, okay, is there any dependency of the stability? Because as I showed that first we did the stability measurement, and indeed there is. So here you see that so we differentiate by some cluster. So each cluster means individually they are not significant. That means, okay, they have some maybe more or less, because for these, as you know, that cells has a lot of like cell variance. So we have to analyze lots of stress granule, like more than 400 stress granule from 3 different replicas, so that we can cover all the biological scenario. And what we found that here, like this is wild type, the partition coefficient is here. So in this reaction, the stability is decreasing. Okay, so here you see that when the stability it is become destabilized, like these all mutants, they are showing higher partition. And again, when like here for I35 the mutant, so this is like the least stable one, again the partition coefficient drops. That means stability definitely has some role to drive this condensation or accumulation in the stress granule, which is really very interesting. And why I'll tell you later. And then what we hypothesize here, that okay, so when we give some heat stress, so what is actually happening? So as I told you, there is protein quality control machinery like chaperones, which is some lots of like other proteins, they work together. We can tell you that this is kind of nurse or doctor of the cell, which are there to help the protein to properly fold, so that they cannot form this aggregated form. So it already exists in this protein quality control system, or chaperone system already exists in the cell. So that is really very interesting. And what happens, so then the question would be, then why we need this stress granule, or why cell evolved this stress granule? So that would be definitely a question. The question is that, okay, in normal condition, if some proteins are already unfolded, for example here, this I35A mutant, this is the least stable. That means it is already unfolded at 37 of our body temperature. So we can imagine that when it is unfolded, the protein quality control machinery can prevent this aggregation. They can bind, and then they can fold back to this native form. But when we give the heat stress, then what happens that lot of like it is too much to clear by this protein quality control machinery. So we hypothesize that maybe when you give the heat stress, the stress granule involved in this or parallelly involved to drive this unfolded protein to this stress granule, and then protein quality control machinery, it would be easy for them to target in this stress granule region so that they can come back to this native form. Okay, so that was our hypothesis, and let's see what our result shows. Yeah, so here what we did by our this fast temperature jump technique, we can calculate the protein folded fraction, unfolded fraction at each like 37 or 43 each temperature, and then we calculated the change. That means 37 our cultivation temperature, and when we give the heat stress 43, like 2-hour heat stress, then how much the unfolded fraction is changing. And then what we did with this, we combined with the hydrophobicity, because this hydrophobicity is one important factor for this non-covalent interaction. And that's why, and when the protein is unfolded, then the hydrophobic residues are coming out, and it has more chance to interact with hydrophobic interaction. And that's why we combine these two terms, and then we try to correlate with the partition coefficient for all these mutants. Because when we are doing this mutation, all this hydrophobicity exposed is different for mutant to mutant. And then what we found almost linear relation, or like we can say like quantitatively that Pearson R is 0.95, which is really great, that we can say that this is really correlated with this, or the partition coefficient or SOD1 enrichment is related with this unfolded fraction in combination with this hydrophobicity exposure. So then our hypothesis is right, and that's why you see here the I35 mutants, to drive, let's go back into this green one, I35, why it is showing low partition again, because due to this reason that you see here, this is the I35, because it is unfolded definitely, but initially as already it is unfolded at 37, protein quality control machinery can drive into this native form. And that's why it is showing, because it do not need to go to the stress granule. But for other, you see that higher partition. So we can say, or we can conclude from here, that heat stress induce extra load of unfolded SOD1 protein paired with this hydrophobicity contribute to this partitioning or engagement in this stress granule region, so that this protein quality control machinery can clear or can target very easily. Okay. Yeah, so now the question is that, okay, does aggregation matter? Because I told this, when the protein become unfolded, it has some chance, or misfolded, it has chance to aggregate. So does aggregation matter for this sequestration or partitioning process? Well, so what we did, we quantify the aggregation. You see like the visual aggregation here for the mutant. So this is for the SOD1. So what we did here, we took two different SOD1, like one is SOD1 full length, and one is this truncated version, or one part of the SOD1 barrel, what mainly we are interested for the stability. And then what we found that for the mutants, so this is for the wild type and this is for the mutants, FOV here, you see the visual aggregation here. And it is known from the literature that the full length mutant, like FOV, form more aggregation. Okay, so here also our result shows these, like wild type, they are almost similar. And the mutants, like this is full length and this is barrel, the percentage of aggregates here for the full length is higher. Okay, but the partition coefficient or this sort of, hello, yeah, okay. So for the like you see the SOD1 enrichment here, it doesn't matter. Like here for the wild type and for the mutants, both are like non-significant. Okay, so full length and barrel. So for these, so this is FOD, these are the mutants, they're similar. So, and here what we found also, like we calculated for this SOD1 barrel, the percentage of aggregation, and other than these FOB mutants, all the mutants you see the aggregation is very similar to the wild type. But if you remember, I showed the partition coefficient, so this is the aggregation, but previously I showed the partition or SOD1 enrichment, they were different for mutants. So what we can conclude that SOD1 recruitment to this stress granule is independent of this aggregation. Okay. So now to quantify the interaction or this protein-protein interaction, or like it could be like protein RNA or other biomolecule interaction, we did some nice technique. It's called like fluorescence recovery after photo bleaching, or FRAP. This is one well-known technique for the biologist or the cell biologist. What we did here, like, so this is the fast channel and this is for the SOD1 value channel. So we chose this trace granule, you see this visual trace granule region, and then we photo bleach. So here there is some fluorescent, and we give some high voltage, high powered laser, so that in this particular region, not whole cell, only in this particular region, the fluorescent protein can be photo bleached permanently. And now what will happen if it is mobile, this protein in this bleach region? Here you can see this, you can imagine this laser pointer is the photo bleach region. Now if I photo bleach for fraction of time, and after that we stop that laser and we take the image like with some time, then sometimes we see that due to this mobility of the protein from the surrounding, this fluorescence can recover. So here you see some fluorescence is here, normalized intensity, and then suddenly it drops. That means due to the photo bleaching, and then we remove that laser and we just take the image, and you see the fluorescence intensity is recovering. Why? Because from the surrounding they are diffusing to this photo bleached region. Okay, and by that method we can precisely quantify their mobility or percentage of mobile fraction or diffusion. Okay, and you see here, so I can tell you that from here, like we can say like the mobile fraction is almost 1. That means they are immediately coming back for this wild type. But for the mutants, so this is for the mutants, you see that here, so here 2 means like inside and outside, inside this region and outside we try to quantify. And you see the inside trace granule region, they are not that mobile. You see the recovery is not that, like it's only recovered like 0.4. That means their mobile fraction is not 100%. Because why? Because they are sticking there due to this protein-protein interaction. And we try to correlate with this with all the mutants, what we showed you already. And indeed, there is good correlation. Like when PC or this partition coefficient is increasing, mobile fraction is decreasing. You see. So what we can tell you that when the protein-protein interact each other, or protein interact with the RNA or other thing in this trace granule, as I told you, these trace granules are mainly built with lots of like protein, RNA, DNA. So we can say this SOD1, particularly the SOD1 mutants, they engage in this trace granule process, or they interact by this protein-protein interaction. That is clear from this study. So with this cell result, we can conclude that heat stress induced. So we can say this native to unfolded fraction, the unfolded fraction mostly engage in this trace granule region, which is good to clear for this chaperone or protein quality control machinery. Now the question is that if we take this simple system, that okay, we just take in the in vitro system, if this unfolded fraction also will show some biasness in this trace granule. So for that we did some simple study, like we take SOD1 barrel protein, fast protein, and just in buffer. And first what we did, we give some heat stress, and also we try to mimic this heat stress condition of the cell, like 43 degrees Celsius, and we try to get this result. So what we see here, like fast form beautiful droplets here or condensate, and then we add this SOD1 protein. And here you see that this is at 23 degrees Celsius for the control experiment for all this like wild type and all these mutants of SOD1. And in this case, like SOD1 is, so this color means this is only for the SOD1. The fuzz is not here fluorescently labeled. And here you see that at 43 degrees Celsius, when you give the heat stress, in this condensate region here you see some black spot. That means there is no SOD1 at room temperature. But when we give the heat stress, you see SOD1 is accumulating in this droplet region, which is kind of supporting our result that we found that in the cell, when we give the heat stress, it is forming this condensation or stress granule in this fuzz region. So similar thing we are found here after heat stress, SOD1 is going in this fuzz condensation. Now let's see our result. If we quantify this partition coefficient exactly how we did in the cell, that calculate the SOD1 enrichment in this stress granule or in this droplet region, what we found here, we found something interesting, or it is kind of unexpected initially, that here this is at 23 degrees Celsius for all these mutants, and the partition coefficient here high means enrichment, low means depletion. So at 23 you see sometimes even depletion, that means SOD1 is not interested to this condensation, but right after heat stress it is increasing right away, like the partition coefficient increasing from 1 to 3, 4 like this. And here you see that wild type here, the native one is showing maximum or highest partition coefficient. So of course then you can tell, okay, in the cell I show you that wild type is showing less and the unfolded proteins are showing higher partition. So yeah, of course this is then opposite behavior. So here if we correlate with the stability, you see there is no correlation like in cell result. Like wild type is showing, which is like the most folded form or most stable form is showing highest partition, but the unfolded form are showing like less partition. So this is definitely like some initially it was puzzling for us, but then yeah, we try to understand why it is happening. So here in the in vitro system, the stability doesn't matter. Rather, protein-protein interaction due to the single point mutation, like it could be like some charge-charge interaction due to this mutation or some hydrophobic interaction, they
please try to conclude, please.
Yeah, sure.
Your time is over. Okay.
Yeah. Okay, I will try to finish soon. Yeah. So then, what we what we conclude here that in the cell stability does matter, whereas in the in vitro system stability doesn't matter. Rather, protein-protein interaction matters. Okay. And yeah, so here you can see for like for all the mutants, even the distribution is different, which indicate that indeed the interaction or the network is different when we did this single point mutation. And yeah, so here, maybe I will just skip this slide, not that important so far. And also we did some study in presence of some cytomimetic agent like some synthetic co-solutes like FeCO, some BSA, which mimic the cellular environment. And here what we found also, I will just go directly, like the stability versus the partition coefficient slide here, the plot. And here you can see that this buffer is this one. And then it is enhancing when we give this like FeCO, and in presence of BSA, it is showing opposite behavior, which indicate that this like the crowded environment indeed matter to drive this partition coefficient. It is not only the general stability ruler that can drive or trigger this SOD1 protein to this partition coefficient. Okay, so with this, I would like to conclude that this SOD1 barrel protein is sufficient for the stress granule association or the condensation. Mainly the destabilized one in the cell are going to this stress granule, which is independent of the aggregation. And mainly in the cell, we can say that this is also due to this homotypic or heterotypic interaction that what we show you by this FRAP measurement. But in the in vitro system, stability, we show that only stability not only playing the role, rather than that the protein-protein interaction, which is definitely obvious, that protein-protein interaction or some electrostatic interaction are the main role to drive these proteins in the stress granule region. And with this, I would like to show you some future perspective. So this is really very interesting result that if we can understand all these biological process like autophagy, like how this protein aggregation can damage particularly some portion to save the cell so that it cannot damage. And if we can understand this LLPS or liquid-liquid phase separation from simple chemistry knowledge, and if we combine all these things with this biological process like how it interacts with the chaperone, with this proteasome, then it would be really, I think, one nice experiment, nice result to understand all these like neurodegenerative disease or all the biological process. So that's why it's really very growing field nowadays to understand this all these process in this scenario. And yeah, if you're interested, you can go this recent published literature, and it was also highlighted in the German magazine, our work here. So with this, I would like to end my presentation, and yeah, let me briefly just acknowledge my previous team, Professor Ebbinghaus, and who are involved in this work here, and yeah, all these our collaborators and the funding agency. And yeah, of course, thank you all for your kind attention. And yeah, I would like to take some questions, or if there's some good question, I'd be happy. Yeah, thanks.
Thanks a lot to Dr. Nirnoy Samanta for his excellent and illuminating talk. Now, I would like to request the participants to put forward just one or two questions, as we are far behind the scheduled time.
May I ask a question?
Yeah, sure.
Dr. Nirnoy?
Yeah, sure.
So, what is the reason to choose SOD1?
Yeah,
for
so
this
that's one good question. Here, we can say that this is kind of model protein in our case, because SOD1 is one globular protein which has like structure, and it can vary the structure due to, I told you, with some mutants. And particularly, we choose for this ALS disease, and both this FAS protein, which is like intrinsically disordered protein, and SOD1 involved in this ALS disease. And so this, you can say that this is one model system for this particular disease, but with this idea that, okay, with this mutation, that protein-protein interaction or the stability could change, and that can show different engagement in this stress granule region. So we can imagine that this is one model system, but this is applicable for also other diseases like Huntington or all the other protein-related diseases.
Okay.
Yeah.
So one thing that is how what is the size of this protein?
Yeah, so this size would be like 2-3 nanometer. Yeah, and the droplets are around some like micron order, but the protein size is like some nanometer order.
Okay.
Yeah, like 2-3 nanometer.
So, thank you very much for your very nice and very informative talk.
Okay,
Thank you.
yeah.
Thank you very much.
Thanks to you also. Yeah.
Thank you, Dr. Samanta.
Yeah, thank you very much.
We are extremely sorry, as due to shortage of time, we had to shorten the interactive part of the lecture sessions. Now we will start our poster and oral sessions. I would like to invite Dr. Shayantani Chatterjee and Dr. Devopam Sinha to chair this session. Please.
Am I audible, ma'am?
Yes.
Yes.
We are already running behind the schedule. Before recalling the name of the participant, I want to mention one thing. Please make your presentation within 5 minutes. Okay. Now, our first participant is Dr. Surojit Jana from Asansol Girls College, Asansol. And next participant is, please be ready, Mr. Aminul Khan from Alia University, and Mr. Virendranath Patro from Vijayagarh Jyotish Rai College. Now, Dr. Surojit Jana, start your presentation.
Hello.
Yes, you are audible.
Am I audible? Okay.
Yes.
So thank you very much for your kind introduction. And today I am going to present my topic on organogen hydrazides and its derivatives. And actually, hydrazine is a ligand containing NN single bond moiety, which is interesting as a bidentate ligand with bind with the metal, and also interesting for the material aspects because NN is having a very weak energy, weak bond actually. So while this organogen like a dialkyl zinc, like a methyl dimethyl zinc or diethyl zinc or diisopropyl zinc, like this kind of dialkyl zinc react with a hydrogen molecule like this NN dimethyl hydrogen under inner atmosphere, It produces actually mainly the tetranuclear zinc hydrazide clusters by eliminating of the alkane elimination, by eliminating alkane, corresponding alkanes like here methane, ethane, or something like it, propane. So this kind of complex is normally they form actually tetranuclear aggregates. The synthesis of various hydrazide derivatives, because in the topic I mentioned that we will talk about the organogen hydrogen in its derivative. If we the synthesis of various hydrazide derivatives normally obtained from one-port synthesis. Like one-port synthesis means a reaction in a one-port mixing together with hydrogen, dialkyl zinc, and other ligands like water or alcohol, or like here is silanol, hydroxylamine, or thiols, those kind of ligands in one port reaction mixture with the appropriate proportion, appropriate reaction mixture, actually appropriate proportion. And to get mainly we got mostly the tetranuclear aggregates. Like for this case like a reaction with dialkyl zinc, hydrogen, and water in approximate proportionate, we got the monohydroxy tris hydrazide, actually there is mistake 3 actually, tris hydrazide aggregates of this compound we obtain. Also if we for this case, like if we react with hydrogen, dialkyl zinc, and ethanol or methanol or other kind of ligand, other kind of alcohol, we got sometimes like a mono alcohol or mono alcoholic or bis alcoholic this alcoholic, this hydrazide clusters with also this tetranuclear cluster, this 4 zinc atom. Also we obtain the tetranuclear cluster with a silanol type of compound, also with a monohydrazide cluster. So all kind of like there is a 4 hydrogen unit, there is a 3 hydrogen unit, there is a mistake 3 actually missing, and there is 2 hydrogen unit with a tetranuclear cluster. Here is 1 hydrogen unit and also tetranuclear cluster. So those kind of aggregation is possible by just changing the appropriate proportions of this reagent in a one-port reaction mixture. Also, if we react with a dialkyl zinc, hydrogen, and also hydroxylamine, we got sometimes like this of pentanuclear cluster with a 5 zinc atom. 5 zinc atom with a pentanuclear cluster where there is 2 hydrogen unit and 4 hydroxylamine unit. So this is a very interesting kind of compound. And also if we react this one-port synthesis protocol like a dialkyl zinc, hydrogen, and thiol ligand, thiol ligand, like thiol ligand, and we obtain this trimeric tetranuclear cluster like this kind of compound we also obtain. Also if we change this hydrogen unit with something different substituent, and also sometimes we can obtain like this of dimeric substituent, dimeric hydrazide clusters, like this is a very simple kind of dimeric structures. So one can react, or one can produce a lot of variety of compound. Also we have also produced something different kind of compound which is a hydrogen like this, or also like a this ring substituted hydrogen like 1-amino piperidine or 1-amino pyrrolidine type of ligand. Also we have tried, and we obtain mostly this tetranuclear cluster. So tetranuclear cluster is very common for this kind of compound, or sometimes also we got sometimes this pentanuclear, trinuclear, or dinuclear or compound also we obtained. Recently actually I have reviewed this compound. This is actually mainly prepared in the groups during my PhD or postdoctoral time, and also recently we reviewed this paper in a new journal of chemistry. So you can go through this paper, and also there are a lot of applications on these compounds on the hydrogen storage application actually. So because these are cluster type of compounds, so one can store some small molecular compound like a nitrogen or nitrogen. So and also we have checked the storage properties of such kind of compounds with the comparison with this like a MOF type of compound, MOF5 or MOF7, MOF5. So we have also published those kind of papers on this kind of compounds, and these compounds are not it's a very sensitive compound because this is organometallic compound. So we have to work on that in the atmosphere to obtain those kind of compounds. So that's all. Thank you very much for your invitation.
Thanks, Dr. Jana,
if any
for
questions.
your nice presentation. Have you any questions, the participants?
Can I ask a question?
Yes.
Okay. Yes.
Okay. It is very interesting work. What is the stability of this complex? How are
This
they?
is very highly stable, but it is echoing actually. So it's very stable compound. We can keep it under ideal atmosphere, but thermally it's very stable. Thermally it's like a 200, 300 degree. It is not decomposing. Up to 200.
It is so stable.
How?
If it is so stable, so how we can use it as a hydrogen storage?
No, actually, we have checked actually. It's not so good like MOF type of compound, MOF5, but like zinc cluster, there is also zinc oxalate cluster on a carboxylic acid cluster, so MOF5. So we have checked those compounds, not all, but few of those compounds for checking the how good that is. But it's not so good like a MOF cluster. But we have checked. There is a possibility of changing some groups or some like the lithium incorporation or halogen type of compounds. Also, there is a lot of compounds inside where there is a lithiated compound, or they are also lithiation, or they are also inside of this methyl or other thing that is also chlorinated also. So we have checked those compounds with this hydrogen absorption properties and compared with this MOF. So there is some kind of study you have done actually, not so fruitful, but not so efficient. You have excellent result we achieved, but we have checked those things, and it's quite something promising actually. Not so good, but it's promising.
One thing, how is it organometallically complex?
Because this is a metal carbon bond. There is RZN group. There all are RZN. Methyl compounds. All are methyl.
These all are okay. I cannot see any methyl or carbon system.
No, actually there is zinc and carbon. All are zinc and carbon, methyl, ethyl. All are organometallic.
Very good. Very interesting work.
Now,
So, Devbong, continue.
now the next participant is Mr. Aminur Khan from Alia University.
Yes, sir.
Aminur,
Yes, sir. I am presenting.
start your presentation
Yes, sir.
and be quick.
Can you hear me, sir?
Yes.
Good afternoon, everyone, and thank you for organizing committee. Today, I will represent my research work on the title mild and efficient synthesis of functional carbazole via Debye assist sequence involve copper and palladium catalyst coupling reaction. Naturally occurring alkaloids, but carbazole alkaloids, first discovered from the curry leaf in 1965, and the first is isolated 1872 from the coal tar. The carbazole nucleus is a prominent structural motif in both the synthetic and naturally occurring alkaloid, which have attracted considerable attention owing to their diverse biological profile. So carbazole synthesis was started in 1888. Pharmacological effect of carbazole are indeed quite variety of, including antimicrobial, anti-tumoral, and antimalarial and anti-platelets. Now, carbazole bearing the electron donating substituent have so high hole transporting efficiency and photo conductivity, thermal stability, and better the electron chemical stability, which makes carbazole units suitable for their application in organic solar cell and organic light emitted diode. Now, the main synthesis targets of carbazole: first condensation, then aromatization. Several methods are reported, mainly without the catalyst, and the main group element of this catalyst. The most efficient and easiest route to fully aromatize carbazole based on the contraction of central pyrrole ring from the tense metal catalyzed CC or CN coupling reaction. A group of scientists involving this method, that is Ullmann coupling, Naroki coupling, and others scientists also developed this. Then the scientists are moved to CN coupling followed by CC coupling and single or double aryl CH activation or on-pot synthesis. Those are used in N-heterocyclic carbene and phosphine ligand or inorganic base. But there is a most limitation for CCN or N or CC coupling. Basically, the costly phosphine ligand and N-heterocyclic carbene and inorganic base, those are destroy the most sensitive functional groups. So we develop of milder condition of two-step with larger functional groups. First, N-arylation of alanine with bronic acid, that is Chellam coupling by using copper catalyst, then intermolecular CH activation to form carbazole by using palladium in ligand-free condition. After collecting various ortho-iodo-N-alanine we start the examine their palladium catalyst intermolecular aryl CH activation with various base and additive and solvent and temperature. We found in maximum yield in palladium acetate 5 mole% and DBU6 equivalent and 100 degrees centigrade in toluene under nitrogen atmosphere. This is the optimum reaction condition. Now, here the main carbazole are found from the functional group involving in the alanine ring also obtains. There is a halogen or electron donating or withdrawing functional groups. Now, here also the bronic acid functional group derivatives also found. Here also the electron withdrawing or donating, and basically the new carbazole also synthesized. The circle indicate the new carbazole I will synthesize. Now the possible mechanism for DBU assist the palladium catalyst aryl CH activation. First, the palladium 2 is reduced via DBU to palladium 0, then oxidative addition of the arylamine, and next proceed to the sigma bond metathesis, and finally reductive elimination we get the desired carbazole product. And achievement, the mild and efficient and practical method, inexpensive and sophisticated phosphine or N-heterocyclic ligand, N-heterocyclic carbene free as well as inorganic base free condition, and DBU act as mild organic base as well as ligand, and prepare 27 carbazoles here also. And basically thankful my supervisor Dr. Shufiul Alam and my lab mate partner. Thank you.
Thank you, Aminur.
Yes, sir.
Aminur,
Now,
Sir.
now, if you have a question, I just take one question.
Aminur, I have a question.
Yes, sir.
There is any reason for the choosing of palladium or copper as the catalyst for CN coupling
Sir, palladium is also better. I will try to copper, but the yield is very low. So the palladium catalyst is easily reduced by DBU and get to the desired product. But I have also copper choose, but this yield is very low.
Yes, yes. Thank you for your nice presentation.
Thank you, sir.
Now, our next participant is Mr. Birendranath Patro from Vijayagarh Jyoti Sai College. And take a note, Mr. Sishendu Gayan from Vivekananda College and Dr. Devabrata Pal from Gokhale Memorial Girls College. Now, Birendranath Patro, please start your presentation.
Good afternoon, everybody. Take just one. Am I audible?
Yes, yes.
Good afternoon, everybody. Thank you, our principal ma'am, webinar coordinator, and organizing committee, and respected and distinguished speaker, and also convener of this webinar for giving this type of opportunity. I will discuss about a carboxylate ligand-based cobalt-2 compound synthesis, X-ray, crystallography, catalytic exploration under homogeneous condition. Epoxide are important compound used in different fields, paint technology, reagents, surfactant, and highly valued synthetic intermediate. Initially, epoxide are formed by transition metal with different type of peroxo compound or oxidant hydroperoxide or hydroxyl benzene, etc. But those compounds are strongly oxidative and environmentally unfriendly and toxic. Those are the problem for this type of oxidation. From this different kind of molecular oxygen as an oxidant, so that they can environment friendly as the oxygen is available very much. For this purpose, we can use different type of transition metal complex, so that the different alkene can be converted into epoxide by using transition metal complex with aerial oxygen. In this case, in this purpose, scientist Mukaya Yamada uses the co-reagent isobutyraldehyde. So we try to this type of copper or cobalt and nickel based compound and to try this type of oxidation. For this purpose, we use cobalt nitrate and
Biren, I think your slide is not showing. I think.
Sorry.
Okay, look.
It's side.
I think slide was showing correct. Are you in the first page or in the second or third slide?
For this purpose, we use cobalt nitrate hexahydrate and also the ligand and heterocyclic base compound and carboxylic base and hydroxyl functional group. This type of complex, we take 2 millimole of ligand and 1 millimole of complex, and in hydrothermal process, this type of complex will form. Here, 2 ligand molecule will attach with cobalt-2 and 4 water molecule will attach for 3D heating in hydrothermal process. Then we determine the structure of this compound and X-ray and FTIR, and also we take the TG analysis. For this purpose, the TG IR of this compound are this type, where the peak, this indicate the presence of water molecule, and this also indicate the this peak indicate the carboxylate functional group. And the crystal structure of compound this type, where pink color shows the cobalt-2 and 4 water molecule attached with this compound, and 2 ligand will attach by carboxylate group. And this is another structure of this compound. This is 1D or 2D structure of this. There are only no covalent. This hydrogen bond interaction will shows it had 1D structure, and this is the one complex with this ball shows the hydrogen bonded interaction structure. Here, this type of interaction will shows the hydrogen bonded interaction of this molecule. Here also this type of hydrogen bonded interaction molecule structure. Thank you. Compound 2 structure. And this is the powder form of X-ray as synthesized and stimulated compound. These are the evidence of this compound, and also this is the TG analysis. This TG analysis we get from the strong evidence that the water molecule will combine with this compound. First, the weight loss was 13.88% in 180 degree to 240 degree centigrade, and second water weight loss is 36%. This indicates the one ligand molecule will loss, and another weight loss was 30%, which indicate that which is lesser than the second one. This is because one oxygen molecule will attach with the metal. The interesting of this compound is the catalytic activity. Catalytic activity of this compound is very interesting. This compound cyclohexene with airflow and catalyst used as a solvent, acetonitrile, and then we get epoxide. Here, here are the main. If we use no catalyst, then the percentage of conversion will only 11%. If we use catalyst 1 milligram, then the percentage is 73%. But if we use 3 gram catalyst and acetonitrile solvent, the percentage of conversion is 96% and selectivity is 93%. Another try to catalytic activity, we use here 5 milligram of catalyst, solvent remains same, where percentage of conversion is increases but selectivity will be decreases. And other solvent we try to define type of solvent like dichloromethane, methanol, acetone, etc. ethanol. We try the maximum or optimum condition for that, the acetonitrile solvent and use of 3 milligram of catalyst at 60 degrees centigrade temperature. If we decrease the temperature, then the plus 40 degree or 50 degree, then the conversion percentage will decreases because of kinetics effect. And have the mechanism of this proposed mechanism of this process. Isobutyl act as an co-reagent which combined with molecular oxygen, free radical is formed. This free radical can convert it into peroxo radical. This peroxo radical convert into peroxide. This peroxide can convert it complex into oxo compound. This oxo compound can convert it or can oxidize to alkene to epoxide, and peroxide can be converted into carboxylic acid. This is from a DFT study. We proposed this type of mechanism, and this is the main object of this work. We successfully synthesized the coordination compound of cobalt nitrate and nickel nitrate and the FTR X-ray, powder X-ray and single crystal X-ray and TG analysis. Complex compound 1 catalytic efficiency much better than others, and we acknowledge this Mr. Dr. Dasarath Pal and Professor Vibhuti Bhushan Sao and Department of Science and Technology, Biotechnology, Government of West Bengal. Thank you.
Thank you, Virendranath. Now, our next participant is Mr. Shishendu Gayan from Vivekananda College.
নেক্সট যারা এ করবে তাদেরকে প্রেজেন্ট করতে বলে, দুজনকে বলে দাও।
Next two participants are Debabrata Pal and Aurobindo Mondol, and then Dr. Chiranjit Pal from Ramananda College. Shishendu, please start your.
Shishendu is not here. Please.
Okay. Now I like to call Dr. Debabrata Pal from Gokhale Memorial Girls College. Dr. Pal is here.
Aurobindo, please.
Yes, sir. Just a minute. Just a second. Good afternoon. This is Aurobindo Mondol from Vivekananda College, and I would like to thank first of all the organizers and coordinator for giving me this opportunity to present my work, and I would like to present my work in the poster form, and which is rule of induction period in determination of the reaction pathway for nanocatalyzed reduction of thiazine dye. In this work, we try to see how the induction period affect the reaction mechanism and rate of reaction, especially nanocatalyzed reaction. And for this purpose, we synthesize nanocatalyst nanoparticle, palladium nanoparticle, by following the literature procedure. And if we take a dye, a methylene green, or which is commonly known as the Mg, and thiazine as a reduced product. So here we see the observation, the K-Ops value, that means observed rate constant, is linearly increases with the increase of palladium nanoparticle amount or concentration, and K-Ops also increases with the increasing concentration of dye, and the corresponding, if we see the K-Ops value with pH, with increasing the pH, K-Ops value also increases. And for the variation of ionic strength, if we plot log K-Ops versus I to the power half, that means square root of I, here we see the corresponding straight line linear, but the plot is negative, which indicates the two interacting species is oppositely charged. And here we see the dye is cationic, so obviously the interacting species, that means the dye is that means thiazine, which is negative in species. And here we see the catalytic reduction of Mg preceded by a time period of delay, that means after addition of nanoparticle, some time is taken, and this time is called the induction period. And the origin of induction period, that means T0, is due to the surface restructuring process, as the surface of nanoparticle is very unstable, and this results the spontaneous as well as the absorb induced surface restructuring process. And the extent of surface restructuring can be measured from the T0, and the corresponding rate of the such restructuring process is taken as the corresponding 1 by T0 or T0 inverse. And here we see the plot of 1 by T0 versus N2H4 display the overall restructuring process, and which is linearly increases with the increase of N2H4, and the intercept here is the corresponding 0 N2H4 presents the rate of spontaneous surface restructuring process, or which is known as a 0 SP OSP, and the plot of 1 by T0 versus 1 by T0 specific versus N2H4 describes only the effect of adsorb induced restructuring process, and the plot of 1 by T0 versus MG shows the rate of total restructuring process, and the plot of 1 by T0 versus 1 by sodium nitrate, that means by measuring the concentration or maintaining the concentration of sodium nitrate, ionic strength is maintained. And from the above observation, we predict this type of mechanism. Then N2H5 plus with react structured at surface catalyst, that is nanoparticle, and then Mg react. And this is our mechanism proposed. Thank you.
Anyone have any question? Okay. Then our next participant is Dr. Chiranjit Pal from Ramananda College.
1 minute. Any more participant is there? Please call them.
Yes. Next participant is Mr. Subhashish Ghosh of University of Bardhaman, and then Dr. Uday Das from Hooghly Mohsin College.
Yes, sir. Am I audible?
Yes, sir.
Just a minute. Yeah. Good afternoon, everybody. Myself, Dr. Chiranjit Pal from Ramananda College, and my topic for this presentation is interaction of methanol diphenol with tetraphenyl porphyrin, a spectroscopic and computational study. Now, the compounds used in this study is a tetraphenyl porphyrin. These are the methanol diphenol compounds. And as you could see in MbDF2, there is a phenyl substitution in the right hand side. In MbDF4, there is a phenyl substitution, and in MbDF5, there is a naphthyl substitution. So these PP and MbDF compounds are very useful in preparation of photovoltaic cell and energy harvesting processes, etc. So coming to the point, now when we interacting with these two compounds, the interaction of substituted methanol dipole system to the electron-rich porphyrin was examined by invisible spectroscopy, and all the methanol dipole derivatives exhibits a strong one-photon absorption in the 50 to 450 nanometer range. And in all the spectra, we get these isosbestic points. We could see in A, B, C, both curves, and this formation of isosbestic point is a proof of formation of stable ground state equilibrium. And this work was done in dichloromethane as a solvent. Now the equilibrium constants are calculated by the Bennett-Hildebrandt equation of this form, and here we get the stable linear plot. So from linearity of this plot, we could say that there is no 1:1 complex formation. The Pearson coefficient and R square value, that is coefficient determination, are also calculated, and that indicates a good fit. Now, coming to the next slide, these are the value of the ground state equilibrium constant. These are the positions of isosbestic point, And from this, you can see that LBDF4 interacts TPP more efficiently in compared to the LBDF2 and LBDF5. And the reason was explored in the next computational section. Now, theoretical studies were done by molecular mechanics and multi-color simulation, and the single point DFT was done by using this basis set. And we solved the global minima, not the local minima. So for this reason, multicolor simulation is important in compared to DFT analysis. Now these are the optimal geometries, and in the optimal geometries, you could see that the pyrolytic photon go towards the fluorine atom of NDBF molecule, and also this group, that is BF2 group, come close to the pyrolytic photon, and this is due to the hydrogen-bonding interaction between the fluorine and the hydrogen atom. And there is also a pi parallel orientation. You can see pi parallel orientation. So there may also occur a charge transfer interaction between the species present. Now here, these are the hydrogen bonding distances, and these are the angle, that is a amount of the image moiety in the plane of the porphyrin ring. And here also there is a pi parallel orientation, and the observed formation constant is not in line with the hydrogen bonding distance, and this is due to the fact there is also a charge transfer interaction, and there both the donor-acceptor charge transfer interaction and the hydrogen bonding interaction plays a vital role in stabilizing this complexes. And in the charge transfer process, if you want to know the direction of charge flow, so you could calculate electrochemical potential, and from the electrochemical potential value, you can get that potential, that is charge, will flow from the higher potential to lower potential, and TP has the higher potential in compared to the methanogen dipeptides. So charge transfer will occur from TP to methanogen dipeptides. Also, to calculate the global electrophilicity index and also global electrophilicity index to predict the electrophile and nucleophile here. So the omega, that is the electrophilicity index greater than 1.5, are considered to be strong electrophiles. So here you can see NDBFs are strong electrophiles in compared to TPP. Electrophilicity index greater than 3 are considered to be strong electrophiles. So TPP is a stronger electrophile in compared to the methanogen dipeptides. Now these are the homologue pictures, and you can see the homoorbital lie mainly on the TPP molecule, and the LUMO orbital side mainly on the methanogen dipeptide molecule. So the charge transfer will occur from HOMO to LUMO, that is TPP to methanogen dipeptides. So in conclusion, you could say that three factors, namely charge transfer, steric conjugation, and hydrogen bonding, play effective role in determining the binding ability, and the electro-rich substituent in methanogen dipeptide with a less steric conjugation favors the binding ability. Now, thank you everyone, and I would like to take this opportunity to express my extensive gratitude to everyone present for their kind attention, and especially want to thank Vijayanagar Jyotish Rai College for conducting this seminar and giving me the opportunity to present here. Thank you everyone.
Thank you, Dr. Paul. Anyone have any question?
I have a question. What is the reason for choice of Monte Carlo simulation for this system?
Because the weakly bonded complex study are done by multicolor simulation, because in this type of study the interaction is not very strong. So if we do the DFT calculation, in DFT calculation we only get the optimal geometry near the starting point. That is, we get a local minima, local energy minima, not a global minima. So if we want to get the global minima, then we need to do multicolor simulation to get the global minimum part.
But we can use GROMACS or this sort of simulation techniques.
Yeah. We could use, but every software is not available to us. So what was available to our lab, we have done this. We could do this. You are right.
Okay. What is the solvent system in this case?
Yeah. So solvent is dichloromethane, CH2Cl2.
Okay. Thank you.
Yeah, thank you, Dr. Naeem. Yeah.
Thank you. Our next participant is Mr. Subhashish Ghosh from University of Bardhaman.
Yes, sir.
Are you here?
Yes, sir.
Yes. Start your
Am I
presentation.
audible?
Yes.
Am I visible, sir?
Yes, you are visible
Hello?
and audible. Yes, you are visible and audible. Start your presentation.
Okay, sir. Myself, Subhashish Ghosh from Bardhaman University, research scholar under the Dr. Devashish Das. Now I am going to start my presentation, which is studies on interaction of azouraceae with transition metal ions, biological and analytical applications. In the first introduction, azo compounds are well-known dye for fabric, paper, leather, and extensively studied for photophysical interaction involving azo-hydrogen tautomerism. Uracil derivatives are more promising for application in medicine, photobiology, and also chemotherapeutic agents. Additionally, biological interaction of divalent metal ions with nucleic acids inspire researchers to investigate potential applications of azouraceal derivatives in biomedical analysis. Next, the objectives work. Our motto is to prepare various azouraceal and azoimines and their transition metal complexes, and to prepare major biological and to find major biological applications, and to find analytical application is in green environment, which is challenging for us, to also find industrial applications. Methodology. The azo-coupling reaction is very simple, mainly used for synthesis of azouraceae. Both ship-based and azo-coupling reactions are used in synthetic procedure of diazoamine. Structure of azo compounds and their metal complexes has been characterized by mass spectroscopy, 1H NMR, and FTIR, and further confirmed by single crystal X-ray study. Here the synthetic protocol, this is very simple. We have first taken primary amine, then it is diazotized at low temperature and coupled with the uracil compound, and to have our ligand compound. Here the characterization of L1, which is our first ligand. Here we can see the azo ligand, which is N-O-N, arrives at 1458.21, indicates the azo is formed. Next, FTIR spectrum of nickel L1 complex. Here also we can see the FTIR spectrum peak nickel nitrogen bond, which is 965. Next, further we confirm the nickel L1 complex with by the single crystal X-ray study. Next, our ligand is L2. Here already we have mentioned the similar process for the formation of the L2 process. Here only the substitution is different. Here the methoxy is used, and the structure is further confirmed by the single crystal X-ray study. Next, also the compounds are characterized by mass spectrum and NMR spectrum. Next, we have prepared the ionic crystal of L2 with zinc chloride and cadmium chloride. Next, the synthetic protocol of L3. It is also like the previous process. Here also we have used paraphenylene diamine in the, and it is diazotized and coupled with the same coupling agent. Next, the FPR spectrum of L3 you can see, and next L3 mass spectrum of L3. Next, the palladium UVV spectrum of palladium and L3 complex. You can see the shift which indicates the palladium complex form, and it is further characterized by FTIR spectrum and confirmed by single crystal extract study that the palladium L3 complex or that palladium azo complex is formed. That is, the palladium azo complex is formed. Significance and scope of our research work. Further study of the worst was innovative design of anti-cancer drugs having less toxics, which is our aim also. Our palladium azo complex and nickel azo complex have shown anti-dengue and anti-cancer activity respectively. After preliminary study and further study will be continued on. Design of bioengineering approaches will be continued. Design of more green industrial and analytical applications because our environment is polluted day by day. Here are some limitations. Global dyestuff industry currently facing major challenges such as high competition, environmental considerations. Here, hence, economical removal of color and toxicity of some waste effluents remains an important problem. This can be reduced and formation is some of the azo compound is formation is time consuming, and some of the azo dye are difficult to produce. Next, thank to everyone for your kind attention and patience. Thank you, sir.
Devbam, now continue. Hello?
Yes. Our next speaker is Dr. Uday Das from Hooghly Mohsin College.
And you also call the other two speaker.
And the next two speaker is Mr. Unutos Patro from Paskula Bonamani College.
Okay.
And Dr. Habibul Beg from Raja N.L. Khan Women's College. Sorry, Dr. Hasibul Beg. Extremely sorry. Dr. Uday, are you here?
Oh, not here, please. Next.
Next, Mr. Unutos Patro. Mr. Patro.
Dr. Uday has joined.
Uday, you are interested to present? Onus, I think Onus will present.
Dr. Uday. Okay, Unutos will present. Unutos, start your presentation quickly.
Anutosh, you are not audible. Anutosh, you are not audible. You are visible but not audible.
Please unmute yourself. Mute করা আছে।
Now I think technical problem.
So can
you will present Dinapam?
Yes, our next Dr. Hasibul Beg. Okay, I think
Hasibul Beg is not here. Please.
Then Mr. Rejaul Karim. Rejaul is there? I think Rejaul is not here.
No.
Then Dr. Pritha Mondol from Krishnanagar Government College.
Yes, sir. I'm here.
Okay, start your presentation.
Is it okay? Audible?
Yes, you're audible and visible.
Yes.
Good afternoon, everyone. The topic of my lecture is thermal denaturation of galectin-1 in silico study. Protein denaturation experiments are popular in protein folding research because this can provide information about the folding intermediates and the denature states. Here we have studied a protein galectin-1. Galectin-1 is a beta-galactoside specific animal lectin with various functions. Native galectin-1 exists as a homodimer of molecular mass 29 kilodalton. The monomer is constituted by one 5-stranded antiparallel front beta sheet and a 6-stranded antiparallel back beta sheet joined by loop regions. This is called the beta sandwich structure of a monomer. We have performed molecular dynamics simulation of galectin-1 at 300, 400, 500 and 600 Kelvin on charm force field installed in Discovery Studio 3.1 platform for 1 nanosecond time period to investigate the stability of beta sheet structure of galectin-1 at high temperature. Different parameters such as root mean square deviation or RMSD, per residue root mean square deviation or RRMS, radius of guidation, surface area calculation and hydrogen bond calculation have been used to monitor the changes of galectin-1 structure at different time point at increasing temperatures. Here is the plot of RMSD and radius of guidation. The figure at the left hand side is for RMSD and at right hand side is for radius of gyration. The figure shows that at 300 Kelvin, after 300 picosecond, RMSD increases up to 6 to 7 angstrom and remains constant up to 1 nanosecond time period. At 400 Kelvin, RMSD gradually increases and attains a value of 9 angstrom. At 500 Kelvin, RMSD reaches to 15 angstrom after 1 nanosecond. When simulation was carried out at 600 Kelvin temperature, RMSD of galectin-1 dimer increases sharply and attains a very high value of 26 angstrom. Radius of gyration calculation also showed similar change in structural compactness with temperature. Calculation of RMSD and radius of gyration together suggests that the complete unfolding of galectin-1 is achieved only at 600 Kelvin temperature, although structural compactness starts to decrease from 400 Kelvin. For further details, we have calculated per residue root mean square deviation or RRMS. The figure shows the RRMS of all 133 residues of galectin-1 in both the subunits, subunit A and subunit B of the dimer after 1 nanosecond simulation at 600 Kelvin temperature. As the figure shows, the average RRMS of the residues of subunit A becomes as high as 23 at 600 Kelvin. Whereas for subunit B, average RRMS of 133 residues is 16 angstrom. In spite of, this is a very interesting observation that in spite of being a homodimer, galectin-1 reveals an asymmetrical pattern of unfolding at 600 Kelvin. Subunit A reveals more perturbation than subunit B in some regions. This asymmetry prevails mainly in the residues 54 to 74, and crystal structure shows that these residues constitute mainly the strand which is farthest from the interface, and some loop regions which joins the front sheet and the back sheet. Next, the RRMS results also shows that in both subunits, the residues which constitute the monomer-monomer interface, that is residue 2 to 7 and 128 to 134, these are least deviated from their initial positions. Galectin-1 is a beta sheet protein, and the stability of beta strands is majorly due to the intra-strand hydrogen bonds of the protein backbone. Side chain hydrogen bonds also contribute to the total stability in the final structure of the protein. To estimate the stability of galectin-1 at different temperatures, the hydrogen bonds involving main chain, only main chain, and as well as the hydrogen bonds involving side chain were calculated. And here is the result. The result shows that the 90% hydrogen bonds are retained during 300 Kelvin simulation. That is, they are dynamically stable. At 400 Kelvin, 80% main chain hydrogen bonds and 50% side chain hydrogen bonds are retained. Loss of side chain hydrogen bonds causes decrease of structural compactness. At 500 Kelvin, almost all side chain hydrogen bonds lost, but 60% main chain hydrogen bonds were retained. And at 600 Kelvin, all hydrogen bonds lost, leading to complete loss of structure. Interestingly, at 500 Kelvin, when 60% backbone hydrogen bonds exist, only 3 interfacial hydrogen bond retained. We have identified the residues of the monomer-monomer interface using a software Profis and calculated the total solvent accessibility of this monomer-monomer interface. The figure shows the result. As the figure shows that at extreme temperature of 600 Kelvin, a large amount of hydrophobic surface becomes exposed to solvent which was buried at this interface. At 500 Kelvin, when all interface hydrogen bonds between two subunits disappear, a large amount of hydrophobic surface remains hidden in the interface. This observation reveals that the stability of dimeric interface is attributed mainly to hydrophobic interaction rather than electrostatic interaction. Snapshots of galectin-1 dimer during simulation. At the left hand side, the snapshots is for galectin-1 at different temperature after 1 nanosecond simulation. As the figure shows that after 1 nanosecond simulation at 300 Kelvin and 400 Kelvin, the sheet structure of native galectin-1 is mostly retained and the two monomers are well associated. At 500 Kelvin, when galectin-1 has lost the compactness of native structure and deformation is observed predominantly in the far from interface region. And at the right hand side, the snapshots is for galectin-1 dimer during simulation at 600 Kelvin at different time points. After only 300 picosecond, we can see that at 600 Kelvin, the galectin-1 dimer has lost its structure, but the two subunits have not gone far apart. Whereas after 500 picosecond, sheet structure of galectin-1 dimer is completely broken down. As a conclusion, we can say complete unfolding of galectin-1 is achieved only at 600 Kelvin, although structural compactness starts to decrease from 400 Kelvin. Side chain hydrogen bonds has important role in building and stabilizing the final structure of galectin-1. Oligomerization imparts stability to the whole galectin-1 structure, the interface stability being largely governed by hydrophobic interactions. The pathway of de-oligomerization reveals asymmetry in dynamical behavior of the far from interface region of two subunits of the protein. Thank you for your attention.
Thank you. Now, our sir, respected Professor Nitin Chattopadhyay, I think any question is, sir. We have any queries?
Peter, now what is the utility of doing all these things at 600 degree K, 600 K? I don't find any utility of it. You see, the important range of interest is from 300 to 400 maximum can be. And then why did you do all these things at 500k, 600k, and one can go that way? This is useless, na?
Actually, sir, previously UVCD studies have been carried out with galactine 1, which exhibited its stability at higher temperatures. So we had facility for
higher means to what extent?
60 degrees centigrade and like this.
Right, 60 degrees centigrade, not 600k, not 600k.
Sir, there are some literature results where some lectins have been studied in this way, like banana lectin. So we thought
useless. You will find so many useless data in literature. Don't go that way. You should ask yourself the question, what am I doing? Why am I doing this? So why? You are supposed to stop yourself after getting the answer why. This is useless, isn't it? Who is going to, or say in which way your protein can go up to 600k? No reason, no way it can go there. The whole living creature will die before that temperature. So what is the use of that thing? Forget about the protein, the whole entity will die, whole living creature will die, isn't it? So please check this thing before you get into the simulation. If it is simulation, you have a package, you can go to any temperature. But it is more important to study within the practical range of temperatures, and not only that. The second question that obviously comes, what are the parameters that you have considered for this simulation? What are the factors that you suppose are going to be changed as temperature goes up? What are the specific factors? Okay, one is obviously structural aspect, and then what else? Structural means geometrical, and then what else? So these things you should ask yourself, and of course your guide. Okay, that's it.
Okay, sir.
Okay, bye.
Now, Unutos?
Yes, sir.
You will present?
Yeah, sir.
Yes, now.
Good afternoon, everyone. Yes. Myself, Unutos Patro. Today, my subject is in silico screening of inhibitors for human DNA polymerase beta to enhance the efficiency of radiation therapy against ovarian cancer. Radiation therapy is one of the treatment choice for the treatment of ovarian cancer. Efficient and redundant DNA repair capacities decrease the effectiveness of radiation therapy. Therefore, DNA repair system proteins are often used as target to increase the efficiency of radiation therapy in cancer treatment. DNA polymerase beta, Pol beta, is involved in single-strand breaks and damage-based repair via base excision repair pathway. Recent studies suggest that Pol beta also play a role in double-strand break repair. Thus, Pol beta might be a potential target to elevate the efficiency of radiation therapy. The three-dimensional structure of Pol beta was generated using Swiss model server. The quality of the predicted model was validated by Ramachandra plot, Pol probability. Further, the druggable sites are predicted, and docking-based virtual screening was performed against drug bank database. Initially, 59 molecules were screened. The selected molecules were further docked using the Doctor web server. Additionally, in silico ADME studies was carried out to find out the drug likeness of the selected molecules using the Swiss ADME server. This is my result, and this is the score. Based on the affinity score, 4 molecules, denufazole, cytidine 5' disphospho beta D xylose, TMC 649128 and balapirivir were selected. And for further study, after checking the ADME properties and other factors, denufazole and cytidine 5' disphospho beta D xylose were excluded. Finally, TMC 649128 and balapirivir are the 2 potential molecules to inhibit Pol beta proteins, as both pass clinical trials on healthy people. In conclusion, radiation therapy efficiency might be enhanced by using these 2 drugs, TMC 649128 and balapirivir, as they potentially target Pol beta protein, act in DNA repair machinery. Thank you.
Thank you, Unugos, for nice presentation. Now I call Rejaul Karim from Alia University. Sir, you have any question?
Yes, a small thing.
Yes.
Do you know what is the Anutosh? Do you know what is the basic way of this radiation therapy? How does it help? How does it kill a cancer cell?
Okay, sir. Actually,
the drugs are only, they just catch the radiation. And then what is the basic reason that the cell dies or DNA is damaged? In most of the cases, it is singlet oxygen. Okay, please go through this. Singlet oxygen is formed in the excited state, and that radiation, that is around 1100 something, that is our DNA cannot bear with that thing, that wavelength. So it is damaged. Okay, that is the.
Hello. Hello, sir.
Yes.
Okay. The main disadvantage of the detection for the ovarian cancer is it can be detected in the very late stage. When we treat only drug, then this can maybe drug resistant. So we use the radiation therapy as the treatment choice.
Yeah. That's all right. My question was, how does radiation therapy help or how does it kill the cell or DNA?
Okay.
That is because, as I said, after catching the radiation, the drug molecule goes in the excited state and it produces singlet oxygen.
ROS formation, this occurs.
Yeah.
Okay, sir.
Yeah. Okay, bye.
Okay, sir. Thank you, sir.
Now, our next person, Rejaul Karim. Okay. Now, one interesting things. All the name of the invited speaker, স্যার আমাদের সবার নামটা এন দিয়ে শুরু হয়েছিল। যাই হোক, sorry. Now we are in the.
So we have come at the conclusion of the program. It has become a little bit lengthy.
Hello, sir.
So Rejaul Karim is here.
I just want to present my presentation.
Yes.
Okay.
Oh, sir, just 1 second. I just some technical issue.
Rejaul, perhaps you have 2 units. Perhaps you have 2 units sitting close by.
Hello, sir. Is it hearable?
Yeah, now we can hear. We can hear you now.
Okay, sir. Okay, sir. How I just. Sir, my presentation is on my desktop, so how I just uploaded this? Sir.
Dosharoth, you can please help him.
Yes, sir.
Sir, you can just advise him.
Sir, I just want to upload my presentation, but there is no option actually.
No, Rajaul, in the bottom of your computer or desktop, do you see some symbols?
Yeah, sir.
So just right to the hand symbol.
Yeah,
there is a box with an arrow inside, right? You click on that. You click on that.
A tab, a window, or sir, something is. Which one, sir?
Yeah, you click on that.
Sir,
you click on that, and then you see a box within a box. So you click on the inner box.
Okay, sir. Just a minute, sir. A window, sir. Okay, sir.
You click on the inner box, and then just now it's coming. Okay, fine.
Okay, thank you, sir. Thank you, sir.
And now at the bottom right, just on the left side of the percentage, there is a cup-like symbol, right? You go there.
Okay, sir. Just a minute.
In the bottom. Yeah. Just click there. Click on this.
Is it okay, sir?
Cup-like thing. No, not. It's not full screen. Just left to the percentage, there is a cup-like symbol, no? Yeah. Click on it. It's not going.
Sir, I just click that on the tab. It is my.
Okay, go on.
Okay, thank you, sir. Thank you so much, sir. So this is I'm Rizal Karim. Hi, I'm from Ali University, and I am going to describe my research work. Just my topic is the mild and efficient synthetic and functionalized carbazole via a DBU assisted sequence involving palladium and copper catalyzed and palladium catalyzed coupling reaction. First of all, I want to represent my presentation with 5 parts. The first part is the definition and fundamental challenges. Second is the biological activity and carbazole and literature study and mechanism of the carbazole synthesis. And third and fourth is the synthesis of channel coupling reaction, the CN coupling reaction, and after that carbazole synthesis and conclusion. The first of all, what is the actual hello?
Yes.
Yeah.
You continue.
Okay. The first of all, what is the organic synthesis? Organic synthesis is like the two organic species which is bonded, which we going to bonded like CN and CC formation of bond, and there is needed some catalyst, solvent, and also there is need of some energy in different variation. It should be, and so this is the first my reaction. This is my actual total scheme actually. But what is the problem is the desired product with the desired product of the formation of the desired product. This is the very difficult problem of the organic synthesis reaction. And second thing is the identification of the desired product. If we going to the reaction, after the reaction, what is our desired product and which is the desired product? There is a many product formation in our reaction, but what is the desired product and right product we don't know. So identification is also difficult, and difficult if the purification is also. So throughout the column chromatography, we're going to the purification. So there is we know that some of two products may be the same polarity. So same polarity come to the very close to close, and that's why the purification through the column chromatography is very difficult. And next is the percentage of yield. Yes, is also it is very much important that if we come to the conclusion, we also describe increase our yield. And fifth is the economical challenges. The economical should be the reaction should be the economical way. And our main challenge is the method of our development methodology should be the eco-friendly way, and also is some hello.
Yes, you are audible. Please go on.
Okay, sir. So this is carbazole moiety, and the carbazole moiety, what is the importance of carbazole moiety? There's a different type of importance in carbazole moiety. They have the biological activity and the photophysical property, antiviral and antioxidant property. There are some example I show in this. This is blue light and green emitting light carbazole. Carbazole is nowadays very important for the solar cell, because solar cell is nowadays very reasonable importance in the research background. So synthesis of the different type of carbazole is very getting very importance. And also there is some anti-HIV,
Vijay, please change your slides.
Okay, sir.
The first slide is there.
Okay, sir. So next is
you click on the left panel and it will come in the main.
Okay, sir. So this is my literature survey. There is so many type of reaction who developed the carbazole synthesis.
Not changing at all. Your slide, it is just your first slide. So please change it.
Sir, I changed the slide in my laptop.
No. If you just click on the left panel. Left panel, you have number of slides.
Sir, is it okay?
Oh, there is some technical problem in
Yes, now it is okay.
Okay,
now it's there. Now it's there.
Is it, sir, okay?
Yes.
And now it's
okay. Okay, sir. This is the importance of I shown that this is the carbazole moiety, and this is the carbazole moiety. There is blue and green and red light carbazole. The carbazole which is used for the photophysical, it has a photophysical property and it should be used in solar cell. But it also some biological activity like anti-HIV, antioxidant property also. And there is some literature survey. Before I going to my research, I also find out research my work that there is lots of synthesis procedure methodology who developed the carbazole formation, and the mechanism is in my research work. The mechanism is the first of all the palladium 0 species, which is formation of the oxidative addition. After the oxidative addition, there is a sigma pallado complex formation. The sigma pallado complex with the bond metastasis, the formation of this B product. And after the B product, the DBU protonated, and after DBU protonated, the 6-member palladium complex is formation, and reductive elimination. After the reductive elimination, there is the carbazole formation, and also the palladium cycle is going on. So DBU here, the DBU act as a base and act as a ligand. The DBU is play a very crucial role in our reaction. So my first scheme is the copper catalyzed Chandlam coupling.
Slide number 7.
Sir, is it okay?
Is it not okay? Just slide number.
Yeah.
Okay.
Yes. Now
it is okay, sir. So this is my first scheme. So my first scheme is is the formation of the Chandlam coupling reaction, the formation N-arylation product. So before the N-arylation product, we going to the 1,2-diiodo Buchwald reaction and Ullmann reaction. So 1,2-diiodo Ullmann reaction and Buchwald reaction have needed the palladium catalyzed, read the palladium catalyzed coupling reaction. So it is very difficult because it needs some temperature and it is very hazardous. So there is some technical problem for the Buchwald and Ullmann coupling reaction. So we going through the Chan-Lamb coupling reaction, because Chan-Lamb coupling reaction is at the room temperature, it is very stable, and it is give us the very different type of substrate. So we get a different type of N-arylation product. Now, sir, is it okay, sir?
Yes.
Okay.
Yes, it's okay, but your time is up. No. Go ahead.
Sir. Okay. Sir. We use the copper catalyzed for the Chan-Lamb coupling reaction, and after that the CH activation. The CH activation is we developed the very different type of carbazole formation, and after the conclusion in the summary, we used the mild DBU as a ligand, and it is very good. It is good for our functionalization group. Okay, sir. Thank you.
Thank you, Rajaul, for nice presentation.
Thank you, sir.
Okay. Now, Anindita, madam.
Yeah, we have come at the conclusion of the program. It has become a little bit lengthy, but hope all of you have enjoyed the webinar a lot. Now I would like to request Dr. Devopam Sinha to deliver the vote of thanks. Over to Devopam.
Thank you, madam. I convey my sincere thanks and gratitude to our principal madam, Dr. Rajyasree Niyogi, for constantly encouraging us to organize such kind of interacting platform. I would like to express my deepest respect and regards to Professor Nithin Chattopadhyay for his highly motivating talk, which I think would etch in the mind of all the participants. I personally feel proud to be part of such an engaging webinar, which taught me personally many aspects of teaching and learning. I would like to thank Professor Shankar Prasad De, Professor N.C. Pramanik, Dr. Naim Sepai, Dr. Nirnay Samanto for their highly vibrant talks. I thank all the participants, including teachers, research scholars, students, for their participation to make this webinar a success. And last but not the least, I thank all my colleagues of Department of Chemistry, my department, for their help and cooperation for making this webinar or arranging with webinar a success. With this, I am concluding the end of this webinar.
Thank you.
Have a good day.
Thank you all.
Thank you, sir.
Thank you very much.
Thank you. Thank you. Now,
Thank you all, Dasarath and all others.
Yes, Sankarda. Now,
long-term interaction, long-term seminar.
arrange the seminar in our college. Okay, to come.
Now we are waiting for physical seminars, physical attendance.
Form.